Murat Bey, duyuyor musunuz beni? Murat Bey, duyuyor musunuz?
Buyurun hocam. Hocam sesim geliyor mu?
Evet, geliyor. Bu katılımcıların arasında bizim panelistler, konuşmacılar da var. Onları bu tarafa
Tamam.
alabilirsek.
Tabii ki. Tabii ki hemen alıyorum hocam.
Roberto Basili, Statistiros. Bunlar panelist pozisyonda konuşmacı arkadaşlar.
Stefano hocamız geldi mi acaba?
Henüz şu anda giriş yapmadı sanıyorum, değil mi Ahmet Cevdet Hocam?
Good morning, everyone.
Good morning.
Bazen isimleri farklı geldiği için göremiyoruz. Hani Rumuz gibi geliyor isimler hocam, nickname gibi geliyor. Teyit edebilirsek en azından.
Spiros'u paneliste al.
Evet, aldım hocam. Şu anda hocalarımızın yetkileri tamamdır. Bir tek Stefano hocamız kaldı.
Hayır, bak, Spiros halen şeyde gözüküyor, attendees'te gözüküyor.
Tamam.
Spiros Statis katıldı. Bu tarafa alındı.
Tamam.
Biraz sistemde bir gecikme var hocam. Onun şeyini yaşıyoruz. Anlık hemen tepki vermiyor. Bilginiz olsun hocam. Hani mikrofon falan geç düşüyor biraz. Kusura bakmayın.
Cevdet Hocam, we are only expecting Dr. Stefano Lorito at the moment, I guess.
Yes, he has sent email to me, and Stefano Lorito confirmed his introduction statements. I think he can join.
Later on, I guess.
I got the email a few minutes ago from him.
Okay, so we are almost ready.
Yes.
Bu arada hocam YouTube'da da yayındayız. Bilginiz olsun hocam.
Okay, thank you.
Thank you.
We have 5 minutes to go.
Good morning. Good morning, Ahmet.
Good morning, Stefano. Welcome to the workshop. Thanks for participation.
Thank you.
Var mı durabilirsiniz? Bir suyla çay alabilir miyiz? Bir suyla çay.
Sohbet şeyi açık YouTube'da.
Hı hı.
Usta hocam.
Buradan da geçireceğim. Kablolar.
Evet, başlayabiliriz Ahmet Cevdet Hocam. We can start now.
Welcome, everybody, to the tsunami session of International Workshop on Active Tectonics and Seismicity of Aegean region, with special emphasis on the Samos earthquake struck on 30 October 2020. Today's schedule, we have 5 presentations. Each presentation will be 20 minutes. The participants can ask questions in 5 minutes after each presentation. And I would like to start with the first presentation. And I would like to give a brief introduction about the presenter. The presentation title is Japanese Experience of Tsunami Hazard from Assessment to Preparedness, Role of Tsunami Engineering Laboratory in Tohoku University, Japan. Presenter, Professor Dr. Fumihiko Imamura, is a faculty member and currently the Director of International Research Institute of Disaster Science in the Tohoku University in Japan. He is an expert on science and technology for tsunami mitigation, tsunami engineering, tsunami warning, and numerical modeling of tsunamis. He has been working on these subjects for more than 35 years. Professor Imamura is one of the 2020 holders of Hamaguchi Award, given by Japan Ministry of Land Infrastructure, Transportation and Tourism. And it is an international award, and it is given to the individuals, organizations that have made significant scientific or pragmatic contribution to the enhancement of coastal resilience against tsunamis, storm surge, and other coastal disasters. I would like to introduce Professor Imamura for his presentation. Here, Professor Imamura, stage is yours.
Thank you very much, Professor Hamadiaratina, and all. Good morning and good afternoon in Japan. So I'm very pleased to join the session related with the tsunami. So I'm going to present my talk by using my slide. So now I'm going to share the slide. Can you see the slide?
Yes, Professor.
Okay, so let me start my talk about the Japanese experiences on tsunami hazard assessment for the preparedness. I a little bit change a little bit title, and the role of the tsunami engineering laboratory in Tohoku University. So in the beginning, I would like to introduce the one international project of the time, Tsunami Inundation Modeling Exchange. It was started in 1991. Tohoku University, especially Tsunami Engineering Laboratory, started to develop the tsunami modeling for the assessment or making the hazard map. In 1980, almost 40 years ago, the Tsunami Symposium was held in 1989. We proposed a new project of the time to the IOC and IUGG conference to transfer the technology of the tsunami modeling. It is called Tsunami, Tohoku University Numerical Analysis Model for the inundation, for making the manual for the simulation and the hazard map and training and conducting the course and inviting the scientist engineer to transfer the technologies. So we started this project. As far as of the last year, you can see the area we transfer the tsunami code to the many countries to cover the tsunami prone areas. So now 24 countries and 48 institutes. So let's start the topics of the 2011 Tohoku earthquake tsunami. 10 years passed since then. The firstly, earthquake happened offshore the Sendai and Tohoku in around here. So the magnitude was exceed the 9.0 almost, and it's fourth largest earthquake in the world. Still, we have the aftershocks until now. So it is a very big earthquake and followed by the tsunami. Japanese government, Japan Meteorological Agency, issued a warning whenever earthquake happened in the coastal area. At the time, also JMA issued a tsunami within 3 minutes to the people in the coastal area. Tsunami arrived to the coastal area almost 20 or 30 minutes. And the tsunami affected this area in Japan and also affecting to the other country in Pacific Ocean. It continued for 2 days. Warning was not canceled for 2 days. So we conducted the tsunami field survey to see what happened along the coast and getting the information of the tsunami record and the tsunami height. We tried to make a simulation, as you can see, generation and propagation to the Sanrik area in the first here, around 20 or 30 minutes. So you can see the big tsunami amplification in the bay. Here, Fukushima, where nuclear power plant is located and very much affected by the tsunami. And the Sendai city is located. Those area in the south was not tsunami prone area. But this time, the earthquake so large extended to the south area and the tsunami affected around here. So now almost 1.5 hours passed, tsunami traveling and propagating to the other area and inundated and run up and coming back to the this ocean area. So we can see the big oscillation for long time. So this is the table of the historical tsunami in Tohoku offshore the Pacific Ocean. We have the database to check the historical document and some report. so reached to this more than 1,000 years back. And we have such kind of the catalog and for the tsunami assessment. And we make a hazard map according to the historical data. So this is the map at the Ofunato in Sanriku area and Sendai city. So blue one is the hazard map before the 2011 by using the historical data. However, 2011 Tohoku earthquake tsunami was so large, so the inundation area more than 2 times or 3 times than the estimated hazard area. So this is the kind of limitation of our historical data for 400 years. So as I mentioned, the Japanese meteorological agency issued a tsunami warning very shortly after detecting the earthquake within the 3 minutes and provide tsunami height and arrival time. So this is the series of the information. First tsunami information was issued just 3 minutes after. This is 14 o'clock 49 minutes with the information with the magnitude 7.9. Actually, this magnitude was so underestimated because the earthquake itself continued for 3 minutes. But at the time, JMA get the data of the earthquake only a few seconds. So that's why they cannot cover the whole earthquake. So this is why of the underestimate. Tsunami forecasting system very much depending on the magnitude in the beginning. So 6 meters in Miyagi Prefecture estimated, and 3 meters in the north, Iwate, and south, Fukushima also predicted. But it was so small, much smaller than the actual tsunami. It sometimes exceeds 30 meters. So it is very underestimated. So, but by using the real-time observation to detect the tsunami at the time by the GPS sensor on the floating buoy. So we can get such kind of information of the real tsunami. That's why the JMA can change or update the tsunami height from the 6 meter to 6 meter to 10 meter or 3 to 6 meter. So time by time, the information is updated. But at the time, tsunami warning is issued, but too late for the people. So this is a big problem and issue for us. So we try to improve by installing the tsunami as well as the seismic sensor offshore around the Tohoku area. So 150 sensors are connected by the fire cable under the sea. So anywhere and anytime earthquake happen and tsunami generated, we can observe and detect those for the tsunami warning. So it is one of, I think, most advanced and dense and good system, I think, in the world. But this is very special. Only in Tohoku that system is available. So other area, we have very limited information with the tsunami real-time histories. So we try to utilize or apply the new way by using the AI, artificial intelligence, to support instant tsunami prediction. So by using such kind of input data, and we calculate many cases with the scenario, AI try to learn many. and get some kind of the output. So even the input data is limited, we can use the AI and to get the tsunami waveform very accurately. So recently we can submit the paper and it was accepted recently, which title is the early forecasting of the tsunami inundation from tsunami and geodetic observation data with a convolutional neural network. It is AI. So this is the coastal area of the Tohoku, and we have the observed data. And we have new detecting system in real time. So we will apply the new way with the AI to the case of 2011 Tohoku earthquake tsunami. So one of the results is the sensitivity analysis for the convolutional neural network with a different observation time with and without geodetic data. So earthquake and change the landform and sea bottom, and next tsunami was generated. So we utilize such kind of the data. So red area is important data for real-time forecasting around here. So time by time, this area becomes large, but not so big. So even we have big system, but we can utilize this area. And this figure showing the accuracy of the estimated tsunami. So actually 10 minutes or 20 minutes, 30 minutes later, red form is the predicted tsunami waveform. And cross observed data on the line, on the land, sorry. And right hand side, it is observed tsunami form. So time by time, we can get good prediction data with the observed one. So this is a good demonstration of the utilized AI, I think. So after the 2011, Tohoku University established a new research institute. It is called the IRIDES, International Research Institute of the Disaster Sciences, with the principle to promote the world-leading research on the natural disaster through the learning from the Tohoku earthquake tsunami to contribute the regional recovery in Tohoku and also other countries internationally, and to set international paradigm on the disaster management studies. We try. And the mission is based upon the practical disaster management cycle like this. Before the disaster happened, after it, we have the emergency response and recovery and reconstructions. So each stages we should have some issue to response. We have sometimes the problem, and we have the good practice, and we try to implement, get such kind of information for the implementations. So this is the our research division of the 7 and 37 the field from natural sciences and engineering and human and social sciences with medical doctors, medical sciences. So this is very interdisciplinary. So now we have the 60 faculty members and 30 the student. So this is the one of the example of the reconstruction process at the Sendai. So this is the situation of the attack of the tsunami, and this is before the attack of the tsunami in Sendai. So actually, Mr. Date, samurai, had a similar experiences 400 years ago in 6001. So they have the big damages by the earthquake tsunami, and he prohibited people to live along the coast. And they put the green belt, pine tree or other, to protect this area. So we followed the idea of the Mr. Date. We try to utilize the green area, but we constructed this time seawall, but as lower as possible. But behind them, we utilize natural resources, and we also utilize infrastructure of the highway elevated, and we constructed the tsunami shelters in this area. And one of the research activity is the some kind of numerical simulation. So this is the example of our result. So this is the typical Sanriku Bay in Tohoku. Tsunami was generated and coming from the bottom, and the front of the tsunami going inside of the bay. So this is very good scenery with the green belt. It is the pine tree, and 70,000 pine tree at the time planted at the time. But the tsunami reached to here and inundated, and erosion we observed, and changed the topography and the geometry, and reached to the city of the Ofunato. So fully inundated, and after that, the negative wave coming. So we can see the back current of the tsunami, and the receded wave we can observe, and again there's some kind of erosion we observed. So this is the new modeling of the tsunami, including the tsunami sediment process. So that by using such kind of numerical technique, we try to contribute to international society with the United Nations and others. So as might you know, the World Tsunami Awareness was started after the 2011, and we support the tsunami evacuation drill, and we make a kind of some brochure for the awareness, and also contribute the numerical model for the real-time the warning by using the good observation data with AI. So after the 2011, we have the international conference for disaster risk reduction at the Sendai by United Nations. So this is the series of the disaster risk reduction conference from Yokohama, Hyogo and Sendai held in 2015. So in the same year, we have the SDGs and Paris Agreement. So 3 agenda, including the Sendai framework for DRR, are very much important now. It is very good purposes, international collaboration until 2030. So this is the outline of the Sendai framework, several outcome and 7 global target and 4 priority actions. So this is the one of priority, which is the build back better in recovery process and rehabilitation and reconstruction. Even though we have the big damages by the earthquake tsunami, we try to enhance our safety by introducing some multi-layer protections. So some artificial structure, seawall, or utilize green infrastructure and utilize the highway and others. So this is good for the tsunami as well as the storm surge and flood. So this is, we hope this is a good example of the resilient city for the other countries. This is the situation of the tsunami, from the tsunami at Sendai. This area was again prohibited to leave the people, and utilized for the industries and some green area for the farming, and then the residential area a little bit back inside of the cities. And we utilize the highway with the steps, so people can easily go up to the highway. And this is also shelters for the people to evacuate in the case. So thank you very much for your attention. So maybe you have the question or some suggestions. So you are very much welcome. And thank you very much for your attention again.
Thank you very much, Professor Imamura. Thank you also summarizing in a on-time presentation from huge experience from Japan, from very old times, from very old times. Thank you very much. So we are waiting for questions from the participants, either from YouTube. I also follow YouTube, or I also follow chat part. Is there any question from participants to Professor Imamura? If there is not any questions, I would like to ask a question, some information from Professor Imamura. There are tsunami breakwaters and there are some gates, closing gates in some parts of Japan. Do you summarize your experience about these tsunami breakwaters and gates closing river mouths?
Closing the rivers?
River mouth, yes.
River mouth, okay.
Yes.
Yeah. So actually, we have the breakwater in the river. Sometimes tsunami come, so we need a gate. But sometimes we need to close the gate in the case of the earthquake happened. But the people, especially the firemen, have to go to the shoreline or coastal area to the close. So it is very much dangerous. So now we introduce or install the automatic close system after detecting the earthquake. So, but this is very advanced, but very high cost. So still we have the limitation to install such automatic system. So otherwise, tsunami can enter the rivers and flood in the backside.
Thank you very much, Professor Imamura. I also ask participants if there is any questions, comments. If there is not any questions, comments, I would like to move to the second presentation. Second presentation will be given by Dr. Roberto Basili, and I would like to introduce Professor Dr. Basili. He is a senior researcher at the National Institute of Geophysics and Volcanology in Italy since 2000. He specialized in tectonic movements, seismic and tsunami hazard analysis. He participated and coordinated the numerous Italian and European research projects. He is currently leading the European node for seismogenic faulting in Italian Joint Research Unit for EPOS. And the title of the presentation is European Fault Source Models for Seismic Hazard and Tsunami Hazard Applications, a focus on the Eastern Mediterranean. So I would like to leave the stage to Dr. Roberto Basili.
Good morning, everyone. I can't find the audio. Can I go share my screen?
Roberto, è nella barra in basso, c'è quel pulsante verde, condividere.
Oh, yeah, I've seen it. Thank you. I've seen it now. Got that. Hope you can see my screen now.
Sì.
Good. First of all, I would like to thanks all the organizers for inviting me, giving me this opportunity today to share some of my recent work in seismic and tsunami hazard in Europe. So I'm going to bring different perspective from previous presentation, going back to the old continent here, and this is the outline of my presentation for today. And when you will be seeing the color changing, it means that my presentation will be getting forward and towards the end at some point, and we'll go through some introductory matter about hazards and faults. What are the state of the art of fault data collection in Europe? How these faults are modeled and used, and then the other uncertainties that we get, especially from seismic sources, and see how we can get better fault source model for future generation of seismic and tsunami hazard. So why hazard? I mean, it's main tool that we have to reduce disaster risk. So this is quite obvious, but others come in many different ways, like different scale and temporal and spatial scales. But all the seismic and tsunami hazard, all the hazard that comes from earthquakes have something in common. That is the geological faults that that generates these earthquakes together with tectonics. And so the main hazards are those by the earthquakes themselves, the ground shaking and tsunami, surface displacement, and also induced earthquakes, and a number of secondary effects that can be generated afterwards by any of these phenomena. And so if we go to the study of faults, whenever a fault generates an earthquake, we can have this different type of hazards with different characteristics that requires also that the faults are mapped and characterized at different level, different scale, spatial scale especially. And today we'll be talking mainly about tsunami, because the section is about tsunami. Give you some hints about ground shaking. We'll not be talking about surface rupture that requires slightly different treatment of the information about geological faults. And so in any other projects, we go through a circle that should be a virtuous circle that goes from promoting and improving the data that we use for the model, and then evaluate the uncertainty, perform the hazards, and then evaluate the sensitivity of what we have used in making these hazard models in a way that we can identify the most critical data sets and parameters and improve the successive round of other calculation, and so in over time to improve progressively our other tools for disaster risk reduction. And what point are we in Europe? These are among the most recent projects in ground shaking hazard to the left and tsunami hazard to the right. Presently, the seismic hazard model is being updated, will probably release during this year, later this year. And these, of course, we're talking about hazard at the continental scale, so very large scale. And in the past, there was very little use of geological faults as an input to seismic tsunami hazard. The main input was the zonations, seismic zonations, And these are two of the most prominent models of seismic zonation for seismic hazard and tsunami hazard in the past. But over the years in Europe, we've been building fault source models. And actually, this one was the first fault source model used for the seismic hazard model in Europe. And again, we're getting to improve. And what is important, we'll see in a minute, that at the moment in Europe, we have a number of regional databases, fault databases, that can help us improve the overall model at the continental scale. And so these are examples of these regional models, and they have been started over the years in different places at different times and are continually updated. And these are main fault databases of crustal faults. And we start having in the latest time also, you start having different models for subduction system. Mainly the Calabrian arc, the Hellenic arc, and the Cyprus arc here. And we're also having lately different alternatives that can also generates alternative models also in the hazard. But how are these fault database built? They are crustal faults and subduction systems are built in slightly different ways. The crustal faults are very simplified at the moment. Basically, there are information gained at the mostly at the surface. So the trace of the fault at the surface is simplified in some way. And this simplified geometry is extruded at depth, usually with a constant dip reaching seismogenic depth. So basically, when we get to the final model that we are able to use as of today, we have a very simplified down deep planar model, and also the trace at the top trace of the faults is very simplified. We know that faults are much more complex than what we see in this sketch here. Similar, but a little bit better situation for subduction system. So usually there is the top of the slab that is modeled using different data. And in this case, in most of the cases here, we are using data, subsurface data. And so the top of the slab is modeled, and then we have to devise some geometrical model for the intra-slab that are mainly useful for ground shaking hazard, not much for tsunami hazard. And so we have to devise at some point what are the limit of the upper and lower limit of the subduction interface, and simulate earthquakes on this interface. So once we add either the surface, the geometry of the fault, either it is a crustal fault or a subduction interface, we can apply different strategies to model individual scenarios that then are built up and merged into, combined into the other evaluation. So usually there is a sort of tessellation or meshing of the fault surface. Then we can generate ruptures with different earthquake sites with variable aspect ratio, and also simulate different nucleation position and slip distribution, and then apply our recurrence model. And from this recurrence model, then we pass all these earthquake scenarios to a further stage of simulation that could either be a physical simulation of a ground shaking, or using a ground motion prediction equation, or making a tsunami simulation, like the topic of this session today. So going back to the tsunami hazard, these are a few examples where we see, once we use all this data, these are examples from the recent tsunami hazard model for the NEAM region. You see here two profiles, one through the Aegean Sea and one in front of the Hellenic Arc. You see that the level of hazard and inundation height, estimated inundation heights here in the vertical scale in these diagrams. And you see for the Aegean Sea, the main inundation heights is just a few meters and much higher in some sector of the in the Ionian Sea in front of the Hellenic Arc. And with this bar, I'm representing here the second and 98th percentile of the epistemic uncertainty in this model. And this epistemic uncertainty is what we want to reduce by improving our knowledge. And certainly the knowledge on faults, that is the primary input, is something that we want to improve. So if this is another recent work that classifies different aspect of for reducing risk and hazard and risk for tsunamis. And we see with the letter S the research gap in seismic sources. And mainly, so in this axis of this diagram, there is the tractability of the source, how we can deal with the improving these research gaps. And on the vertical axis, which is the sensitivity of the hazard and risk to these research gaps. So basically, you see that we are more sensitive to lack of data for limited knowledge of past events. So certainly can be improved. But also we have lack of both data and theory for a number of other aspects that regards the seismic source. And mainly we'll be looking at the identification of the sources, strong sensitivity, and also some of the variety and complexity of the sources that also has high sensitivity, and also it's harder to treat and to deal with. And so identifying faults, one of the best way is to use multi-scale geophysical data. So basically, depending on the type of acquisition of this data, if we have higher penetration of the acquisition, we can see how the fault is at seismogenic depth. And with high resolution acquisition, we can only see the shallower part of the faults and characterize some other aspects of the faults. For example, the displacement of recent sediments and the activity in recent times. So as you can see here, is depicted the same. If you look at the central horses, the same place imaged by different types of acquisition, and give us the opportunity to trace back the geometry and activity of the faults at all scale and at all the depth extension of the fault itself. And so again, if we want to characterize the full three-dimensional aspect of the faults, we need to use lots of seismic reflection data. This is an example where with this, you see here the number of 2D seismic lines that are being used to get to this model of faults here. And certainly in this way, we can retrieve the geometrical complexity of the faults. And this is what happens when we compare at fault for which we know the geometrical complexity with respect to a fault at simply, very simple model of a fault with a plane. So we have here an example of two end members. So on the left-hand side, you see a planar fault with homogeneous lip distribution on it. And this is the tsunami propagation that we obtain with a simulation. In this other case, we see what we get when we use the complex fault that you see depicted in this diagram, in this oblique view here, with also at a variable heterogeneous slip distribution on the fault surface. And you can see from this image that for the same earthquake, I mean, same moment magnitude, same hypocentral location, and same average geometric parameter like strike, dip, and rake, and average slip, we get two totally different, very different tsunami scenarios. So this just two remarks that it's very important that we are able to build realistic geometry of the faults. The same applies to ground shaking. If we consider different geometry, the same earthquakes, and we see also an effects in the ground shaking with peak ground motion up to 2.5 times higher if we are using a curved faults with respect to a planar fault. And another underexplored aspect of crustal faults is the distribution of the slip rate at depth. Usually in other applications, we use an average slip rate distribution that is uniform in the down dip direction. And we can imagine that if we use a variable slip rate distribution on the faults, so if the slip rate is higher toward the surface, we get different effects when the slip rate is higher at the deeper parts of the faults. And subduction sources, again, complexity. We can retrieve geometric complexities from seismic reflection line. This is a recent example of the Calabrian arc. Sorry. And obviously, treating this data, we have uncertainty due to the velocity model that we adopt to make the depth conversion of the data and retrieve the geometry of the shallow interface. And this is what happens when we compare earthquakes, potential earthquakes on the subduction interface. This is an example of 3 different earthquakes. In this case, on the left-hand side, you see the complex geometry, and on the right-hand side here, the planar geometry with 3 different earthquake magnitudes, 7.5, 8, and 8.5. This is the same subduction modeled with the complex geometry and the planar geometry. And this is the effect, and we see the effects in the Central Eastern Mediterranean in a number of points here, Southern Italy, Northern Libya, Northern Africa, in Libya, and Greece, that the effects are very variable with peak of over 40% in individual of tsunami amplitude in individual scenarios. And we can see if we aggregate all these uncertainty into another model, we are going to get an uncertainty in the final results. Again, if we instead of having uniform slip on the fault surface, we apply not only at 3D geometry, but also heterogeneous slip on the subduction on the slab interface. We get different results. In particular, here we show what happens if we consider the dependence of the slip distribution on the variation of rigidity with depth. There are some works that tells us that the rigidity increases with depth in subduction zones, and when we increase it, or we lower the rigidity upward a shallower depth, we have to compensate with for the same rupture area, we have to compensate with slip. So we have an effect of amplification of the slip toward the surface. And so you can compare the slip distribution in one case when we use the depth dependence of the rigidity with depth, we get to this type of slip distribution with amplification of the slip toward the surface. Here the subduction interface is dipping toward the northwest. And this is without considering the dependence of the rigidity with depth. And when we aggregate a number of many scenarios into an other model, these are the other curves that we get at 3 sample localities in the Eastern Mediterranean. So the source is again the Calabrian arc that is here. So this is in the near field, and progressively in the far field in Greece and Cyprus. The red line in this curve, so this is the probability of exceedance, and this is the tsunami maximum inundation height. And so with red, we see the other curve resulting by the depth dependent set. So the earthquakes with the shallow slip amplifications in the scenarios, and in the blue, the other curve, the corresponding other curves for the same earthquake set without considering the variation of rigidity with depth. And what we see here, if we cut these other curves at different average return periods, we see that the depth dependent set, we obtain much higher maximum inundation height in the near field, in the far field the same, in the very far field is again the same. And we can also see that the progressively also and that we can have different models depending on what type of depth dependence we model, how we model this rigidity variation with depth. And if we consider a different level of maximum inundation heights, we see that with the depth dependence yields lower probability for lower maximum inundation height and higher probability if we go the other way around from maximum inundation height to probability at higher intensities, we obtain also higher probability for larger other intensities. And so this is pretty much everything I have for today. Just few take-home thoughts. And so we know in Europe, fault sources are increasing in use. So in both seismic hazard and tsunami hazard applications. And so there is a demand for improving also the fault sources, the characterization of the fault sources. At the moment, the existing models are very simplified, and we know that the characterization of the fault source is a primary research gap in this application, and we are seeing today some example of how the complexity that we can model affect the individual seismic scenarios, even the final hazards. And then my suggestion is that multi-scale geophysical data is an indispensable tool to fill this research gap and improve our knowledge of faults. And then we know that we are able to simulate most of this complexity, and its time is ripe to improve the fault sources, to move towards a new generation of other models for the future. Thank you very much for attending.
Thank you, Dr. Basili. Now I wait questions from the participants. Is there any questions from the chat or from YouTube? I follow both. Just waiting for the questions. I would like to ask Dr. Basili, first of all, thank you for your presentation and participation. How is the relation between your explanation about the earthquake simulation techniques with the seismic network? Does it need much more instrumentation in seismicity?
No, mainly I'm referring to active seismics. So with artificial seismic sources and mainly same techniques used by the oil industry to retrieve subsurface data.
I see.
Okay.
Thank you very much. I check YouTube channel and our chat channel. There is no questions, and if there is no questions, I would like to ask Dr. Vasily first. Thanks for his presentation, and also I ask him to chair the session for the next presentation. Thank you, Dr. Vasily, and stage is yours as the chair.
Yeah, thank you. I have to switch to now. Where is my control?
In alto.
Yeah. So stop sharing. Okay. So I'm taking on this, sharing this session to give the floor in a minute to Professor Yeltsin, and Professor Yeltsin is a faculty member of the Middle East Technical University in Ankara, Turkey, and in the Department of Civil Engineering and Coastal and Ocean Engineers. He has a long term on tsunami, storm surges, design of coastal structure, and physical numerical modeling. And I was honored to work with him in several, in a few European projects. He has participated and coordinated both Turkish and European research projects, and he is presently one of the 2020 holders of the Yamaguchi Award given by the Ministry of Land, Infrastructure and Transportation and Tourism in Japan. And so time to give the floor to Professor Yeltsin. And so the floor is yours. Please share your screen.
Thank you, Dr. Vasily. I hope my screen is available. Yes. The presentation title is Realities, Achievements and Requirements for Tsunamis in Eastern Mediterranean and Aegean region. And in my presentation, just in the beginning, I have to acknowledge numerous organizations and also companies, and also the people, scientists, from scientists to the general public. There are many contributions behind this presentation. Earthquake and tsunamis in Mediterranean Aegean region. We know that Mediterranean and Aegean is the start of the civilizations, and we know over more than 4,000 years the instrumental seismicity in the last 100 years or more. There are many important cities in the Middle East have destroyed by the earthquakes, and some of them by tsunamis. And the Santorini eruption and the decline of Minoan civilization is one of the important and oldest examples of the tsunami volcano activity in the event. And Santorini, as we know that, and some other active volcanoes in Aegean Sea should be considered as the some of the hazard studies. We have made paleo tsunami studies in the Aegean Sea, many located publications, but in the first attempt many years ago, Turkish, Greek, and Japanese scientists, we have found the traces of the tsunamis in the region Didima at the west of Turkey, and the site was untouched sites, and we could find the traces of tsunamis. Marine sediments was at the bottom of the trench and trench layer. Pumice from Santorini and volcanic ash came from atmosphere and deposited onto the other layers. And we all know this is the simple presentation of the tectonic activity, plate tectonics. And the left figure is the general characteristics of the faults in the Aegean Sea from the respective website from Greece, and right figure is developed from the two different publications. This is the figure possible sources extracted from the publication Altınok et al. 2011, which provides detailed information about each event in the coastline surrounding Anatolia. This is the figure showing in the since 1900. Black points are the earthquakes greater than 6, and red points earthquakes greater than 7. And I would like to point out some earthquakes in the Eastern Aegean, because we experienced numerous earthquakes greater than 6 magnitude, and they also generated small or moderate tsunamis since 2014. 2014 was the event 6.8 happened at northern Aegean at the west part of Gökçeada in Rhodes Island. And after that, in 2017, we experienced another earthquake in the Central East Aegean, 2017, south of Lesbos Island. And 2017 July, there was an earthquake that caused 2 casualty, but it generated tsunami, local tsunami, between Bodrum and Kos towns of Turkey and Greece. And we see that there are some motion and earthquake activity in the region, and we experienced another one is 30 October 2020, north of Samos Island, which showed the real face of tsunami, and reality is now common. And it is also everybody witnessed this reality. And when we go back to 1944 or 1867, from Altınok et al. 2012 indicated 2 small tsunamis in the region. And next slide also shows that 1949 and 1881 are the 2 small tsunamis happened in the Kios Karaburun region and also Çeşme region of Turkey and Greece, north of the recent earthquake. And Aegean Sea tsunamis in the last decade, I have summarized, or I have given information about those, and this slide summarizes their main and brief information. And July 20, 2017, Bodrum coast earthquake caused damage in Bodrum, southern part of Bodrum Peninsula and north part of the Kos Island in Greece. And these are the photographs taken after the event from Bodrum and Gümbet Bay. The photograph seen here is the right middle part, is the recedence of the water in Gümbet Bay. It is clearly very abnormal condition, and it shows the face of tsunami. And similar affairs happened in the coast island, and some photographs from coast island. And analysis of 30 October 2020 Aegean tsunami and how can we prepare ourselves for future. We have seen that there is low response and not receiving the tsunami warning. But now tsunami warning issued 11 minutes after the earthquake by query, and also similarly by NOAA Greece. And there were limited modeling efforts for the impacted area, but after the disaster, we motivated to focus and join our forces to understand better what happened and what will happen in the Aegean Sea in terms of tsunamis. And there were efforts in UNESCO, IOC, Northeast Atlantic and the Mediterranean and also connected seas tsunami warning system. The Kandil Observatory is one of the participants, one of the tsunami service provider, together with IIGV and together with other organizations. I will show this, those in the later slides when I come to the achievements section. And Query has issued the warning after the 11 minutes after the earthquake in 30 October 2020 event. And this is the messages released by Query. And it was very abnormal because even if Aegean Sea is small and not so deep sea, the tsunami happened and we witnessed tsunami in the region. 110 kilometers long coastline affected by tsunami motion. And 2017 event was a reminder, and there had been different field surveys performed in 2017 event and also in 2020 event by support of mainly companies and also TÜBİTAK after the event. And the post-tsunami field surveys are very important to understand not only the motion of the wave and the damage level and reason of the damages, but also understand the mechanism that generated tsunami. So that is important. And we perform two field surveys in the area affected in Turkish coast by tsunami. And the coming slides are summary of the information gained from the surveys. The tsunami penetrated along the small river. It is called Azmak in Turkish, Alaçatı Azmak, 1,160 meters above drag into this position, and the total penetration distance was about 2.5 kilometers in Alaçatı Azmak. And this is the front part, seaside entrance of the Azmak. We see that there was 1.7 meter water level increase, and it happened 35 minutes after the earthquake. And the panoramic view of Zeytineli. Zeytineli is a small bay. There is a very interesting resemblance or similarities between Japanese impacted areas and impacted areas in Aegean Sea with the recent tsunami. There are bays, and the bays ends with a river mouth or a small rivers, and tsunami penetrates into the lowland area along the river, and it causes damage and inundation in that area. Similar figures are seen here, but the scale is very much different from Japan and Aegean cases. These are other photographs from the same place, and the main action and main impact has been observed in the Teos Marina. Teos is the ancient city. It has had two ports, and both ports in this tsunami have been affected by the tsunami. Teos Marina, this is the modern marina located on the north port of the Teos ancient city. Distribution of the flow depth and the run-up are shown on the figure here, and the effects of tsunami and is illustrated by these photographs. In order to save time, I would like to go faster with these slides, but when the presentation is available, everybody can review and ask more questions by email to me later. These are the poorly engineered structures fully damaged by tsunami moderating. And maximum tsunami height has run up to 0.4 meter in Zeytineli. And Akarca is a small village south of Sığacık. 3.8 meter is the maximum value. Inundation distance in Zeytineli reached to 760 meters. And maximum penetration is Alaçatı Azmak small river, 2.5 kilometers. And there are engineering codes and guidelines have been finished in 2016 in Turkey, and there should be much more information to be added to the guidelines in terms of tsunamis and also maybe cyclones and storm surges. Public education awareness, evacuation plans are necessary. I will show some achievements later to you. An example roadmap specific to Izmir province is one of the examples we have prepared, considering earthquake, flood, landslide, tsunami, fire, and other climate change and other hazard types. For the case of 30 October 2020, we also made simulations of past events, and we use our modeling efforts to understand hazards and estimate run-ups and assigning the priority to specific areas. This is the result of simulation shown. Left one is the large area and right one is the small area, and the water recedence observed in the beginning, and you will see the inundation at right figure, mainly in Sığacık, first sea recedence, and inundation continued after that during the event. This is the distribution of the inundated areas, lowland areas near the coastal area have inundated. I can point out that this is the point that Teos South Marina, it is now ancient archaeological site, and it has been inundated during the tsunami, and Teos North Marina on the north part, modern marina and Sığacık town has inundated. And the achievements, UNESCO achieved the establishment of the tsunami warning system in the Northeast Atlantic and Mediterranean. Here are the 5 tsunami service providers operating, accredited, and operating in accordance with each other, serving to tsunami service in the region. From west to east, Portugal, IPMA, France, Senal, Italy, INGV, Greece, NOAA, and Turkey, COERI, are working and issuing tsunami warning messages. And the main duties and mandate of the tsunami warning system in the Mediterranean are listed here. And also it is working with full force and improved and significantly. These are the list of mandate of the Northeast Atlantic, Mediterranean, and tsunami warning system. And final example from the achievements for the achievements from Istanbul is given here in the final slides. The hazard level must be computed. And Istanbul Metropolitan Municipality requested project from our institution, and we have been working with Istanbul Metropolitan Municipality since 2018, and we achieved to finalize complete tsunami hazard assessment, vulnerability and risk analysis, and also tsunami action plan for the Marmara Coast of Metropolitan City of Istanbul. These are the different district maps, tsunami hazard maps, and also tsunami risk maps. Using the vulnerability analysis, we have developed the tsunami evacuation maps, and we have also tested some of the structural measures to protect the inland area from tsunamis. There are some structural modifications may help, and these slides shows the results of the structural measures and for the decision makers. And non-structural measures are much more important because it is easy and we should follow all these, and there are many information in the reports. Also it is available in the web about the non-structural measures. Tsunami evacuation guides and tsunami post-tsunami survey guides are given in those reports. And finally, I again acknowledge the supporters behind this presentation. And there are many references I put here. If anybody wants to follow the presentation later, these very valuable references will help everybody. Thanks for your kind attention.
Thank you, Professor Yeltsin. And checking if there is any questions written in the chat. Apparently, at the moment, I don't see any questions. Oh, yes, something is coming up. So one question, somebody's Turkish name, I'm not sure I can pronounce it well. Dokchat Sayar is asking, is it expected to see more other classified as tsunami in the countries where there is not many tsunamis happened before, as in Turkey, with the progress of the climate change?
I also check. Okay, climate change. Yes, question is thanks for the question. Climate change is an important issue. It will increase the water level, but tsunami behavior, where we expect that 1 meter water level increase in the coming 100 years, will make long-term water level, sea level change. It requires adaptation. But tsunami is much more instantaneous events than climate change, long-term water level rise. So we should expect tsunami occurrence in the future by looking at the history. However, there is no clear relation between the climate change and the tsunami occurrence because both depend on different forcing events.
Yeah, so I'm not sure if we have time for another question. I don't see more questions coming. So I ask the organizers if we can proceed further. Well, I think we can proceed first. So first of all, I thank you once again, Professor Yeltsiner, for your presentations, and I'm returning you the chair of the session to carry on with the other presenters. Thank you very much.
Thank you, Dr. Basili. Thanks for the questions. And now we are going to move to next presenter, Dr. Stefano Lorito. Dr. Stefano Lorito is a senior researcher in geophysics at the National Institute of Geophysics and Volcanology in Italy. He is a member of the coordination body of the Italian Tsunami Early Warning System. He has been vice chair of the Intergovernmental Coordination Group of Northeast Atlantic Mediterranean Tsunami Warning System of UNESCO. His major research interests are tsunami sources from joint inversion of geophysical data, tsunami hazard methods, and analysis tsunami warning methods. He has been involved with different roles in several key tsunami European and national research projects. And I would like to announce the presentation title, Tsunami Hazard Warning and Risk Reduction in Italy and in the Mediterranean Sea. And please, Dr. Lorito, stage is yours.
Thank you, Professor Yeltsiner. I hope you can see my presentation on screen now and,
it is clear.
And hear me. Thank you. It's a great honor to be here with so many esteemed colleagues and friends with whom we have cooperated in the past, and we will keep surely collaborating in the future. So my presentation will start with really brief overview of the NIA-TWS system in a couple of slides, but Professor Yeltsiner has covered it. And he was even my chair when I was vice chair, so I feel humbled here. Okay, and then I will focus mostly on the developments that are going on in Italy, mainly for tsunami risk reduction, by trying to highlight here and there important points, in my opinion, and gaps that we should work to fill in the future, to continue this journey towards tsunami risk reduction. So let me see if, okay, it works. So let's say that as a community, we have been working for about 15 years now with strong inputs given by the 2004 Sumatra Andaman earthquake and Indian Ocean tsunami, and since then the NIA-TWS was formally established, and of course it received another great impulse by the other big disaster of Tohoku, which Professor Mamura has talked about. And the principle is probably has been also the strategy of the NIAM has been presented by Professor Yeltsiner, but the principles are also summarized by this very famous picture that I like to read as a combination of early warning implementation and within parallel a risk-informed coastal planning and preparation and awareness activities to make it work. And to conclude, the already mentioned accreditation of the five tsunami service providers and the earthquake source zone that's monitored by us for earthquakes of magnitude 5.5 and higher. So I consider this a substantial and successful effort, particularly if we consider that we live in a region where the phenomenon is relatively less frequent than in other regions. And let me also underline that this effort has involved great contribution by the IOC UNESCO member states in several respects, from infrastructural to legal to also scientific and technological effort and development. And the tsunami warning in the NEAM region, or East Atlantic, Mediterranean connected seas region, is based on early seismic detection and characterization. So the tsunami is not directly measured, and most of the coasts lie in the near field of the seismic sources. And then the sea level data, coastal sea level data, mainly are used for confirmation or cancellation of depending on the cases, of the tsunami warning messages. And if we want to focus on the gaps with a constructive idea of trying to improve the system, is quite evident that there is a instrumental gap toward the southern side of the region, and said only seismometers are used, but GNSS data are going to be integrated thanks to different efforts. And regarding the tsunami measurements, at the minute there are some efforts for developing cable sensors network to reduce the time for warning, to increase the lead time for evacuation. And another delicate point with 5 operating tsunami service providers in the region is the interoperability among them, on which we are all working. Okay, and the tsunami forecasting is presently mostly based on decision matrices like this. So the magnitude and the epicenter location are used to form the alert levels that can be roughly speaking, land threat or coastal and marine threat, or only an information message if the tsunami threat is not considered significant. And of course, there are things that can be improved in this respect, because let's say the uncertainty treatment in the decision matrices is somehow implicit, and let me call it respectfully call it simplistic, because there is a circle around the hypocenter, and the alert level depends on the distance. So source and bathymetry directivity effects are neglected. So in the attempt of sitting on the worst case side for obvious reasons, but sometimes due to these directive effects, for example, even missed alarms are possible, not only false alarms due to conservatism. And in a way, such an approach mixes the scientific action of the tsunami forecasting with the political decision embedded in a tsunami warning. So there is a not totally transparent balance of the roles, and there might be some confusion of roles. So to improve the two aspects, it would be better to be able to distinguish between the tsunami forecasting and alerting, depending on thresholds that might be set for political reasons. But okay, the system worked and is working very well, as Professor Yassiner has illustrated before me. This is the same slide actually that reports the activations that we had since 2017 for a range of magnitude between 5.7 and 7, and all the messages were sent out between 7 and 10 minutes, and the other centers performed consistently. Let's say this is only an example from our center, from the Italian CAT, Centro Allerta Tsunami. And also for the 30 October Samos tsunami, warning message was issued with a local watch after 8 minutes from INGB, where and then the tsunami exceeded 2 meters, for example, and also significant inundation distances were observed as previously presented and as reported in this paper by Dugan and co-authors. Another side of the story is the hazard modeling. We perform hazard modeling across really hazard modeling and hazard mapping across many different scales with different purposes, starting from the global, going through the regional model presented by Dr. Basili before, that was funded by DG ECO and is becoming a reference model in the region as a basis for homogeneous planning or as a driver for prioritization of the further local hazard and risk assessments. And going down with the scales, we are and we have been and we are working in the CHEESE project that is trying to establish a center of excellence for exascale supercomputing in the area of solid earth, in which we are delivering pilot demonstrators, let's say user-friendly pilot demonstrator to access HPC resources for exploring the uncertainty as described by many tsunami scenarios for local high resolution hazard assessments. And in all these scales, the scheme is probably almost the same. The ingredients are the probabilistic earthquake model and the tsunami simulations for the tsunamis generated by all the members, all the scenarios describing forming the probabilistic earthquake model. And for full uncertainty exploration, each of these applications may require a really significant number of simulations here conducted on single GPUs, also thanks to some PRAISE projects or the support by Cineca with the Tsunami IC code provided by University of Malaga. And one difficulty or one challenge, let's say, is that because these tsunamis are rare events, that there is sparse and heterogeneous evidence, so we rely, say, on source probability from relatively short catalogs, which increases the uncertainty, particularly for large tsunami events. And there is also some lack of understanding regarding the process. For example, the frequency of tsunami earthquakes or even the non-seismic sources. Sometimes high resolution near coast bathymetry is not available, and of course there is a need for important computational resources, and probably also to better address the uncertainty related to the numerical modeling itself and through, for example, sensitivity modeling. But in all cases, the hazard is represented by hazard curves representing the probability of exceedance, for example, of inundation height, and the different curves of the model. And then these curves can be used in various ways to produce maps for different average return periods, or probability maps related to specific heights. For example, the probability of exceeding 1 meter height somewhere. In Italy, in particular, these curves at coastal locations were used for the official indications for coastal planning and evacuation planning. An average return period of 2,500 years was chosen, and quite high percentile of the epistemic uncertainty, the 84th, was chosen, and some safety factors were applied on the top of it before applying an approximated rule for coastal attenuation to end up with the inundation maps all along the coasts of Italy, in a collaboration of INGV, the Civil Protection, the National Civil Protection Department, and ISPRA, the Institution for the Environmental Research in Italy. And yes, the uncertainties are important here and must be and are not to be neglected. And this is the reason for the safety factors. We keep checking whether the approaches are reasonable within our current understanding of the uncertainties. And so we test it, and they seems at the moment, the approach seems at the moment to stand to be quite robust for the purpose of designing evacuation maps. So the process slowly started, and there are already examples of last mile implementation in different locations here, Palma in Calabria, Minturno in Lazio, where they are already designing the evacuation routes. Maybe the figure is a bit small, but there are already identified the single streets depending on the level of alert for the evacuation. And in the context of awareness raising, a big effort is being done by INGV through the website to publish continuously news, to increase the awareness of people. So this is a report of how many were published recently. And also another aspect being investigated is the risk perception, in order to tailor the risk reduction measure on the perception of the risk by the citizens. So a series of surveys becoming really massive and extensive, with thousands of people interviewed along all the coast of Italy now. Also, the Tsunami Ready program endorsed by IOC UNESCO has officially started in Italy, and this is a document proving it. So you all know about Tsunami Ready. Is an integrated program involving different levels, but the local communities through boards of locals. And I think I can, I don't know if I'm in time or more or less, I think, yes, I now come two conclusions. So while I was preparing the presentation, I was a little bit afraid of describing in a too negative way all these gaps, but actually I tried to highlight but also all the ongoing efforts to really implement the last mile of the system and an end-to-end system. So the dissemination of the messages to at least the Italian territories, but this is true also for other countries, is not complete, but cell broadcasting is being implemented, also the local disseminations like science and other things. The local civil protection plans have not been updated yet everywhere, only at a few places, but the process has started responding to the national directive. The surveys identified limited awareness and probably as a consequence also of having the local plans still under implementation, the preparation to react to warning messages is still limited, and so we must work on it, and we are working on it, and Tsunami Ready is one of the answers to these issues. Professor Yassine has beautifully explained that planning should be based not on a single hazard assessment only, but a multi-hazard perspective should be envisaged at some point. And generally, risk assessment is just starting. So we are still at the level of hazard assessment, so not for people, not for lives or buildings or even critical infrastructure, except for some local examples. But Italy is planning the national risk assessment starting next, for tsunamis starting next year. And of course, we struggle every day with certain level of absence of long-term sustainability planning for such a complex and important end-to-end system, because we don't have tsunamis every day. That can be one of the causes. And that's it from my side. I just want to highlight 3 papers if some of you want to read further about gaps in this type of considerations. The Amato et al. Paper already mentioned on seismological research letters also discusses the trade-off between the earthquake characterization accuracy and the speed. So what happens if you use a solution that you have after 2, 5, or 8 minutes, and there is an analysis of this, and probably we will adapt our system following these findings. There is also, this study has been already mentioned by Dr. Basili about the scientific gaps, research gaps, but also the tools available for calculating tsunami hazard and risk, and the non-subduction, non-seismic sources that we need to deal with in our region, including landslides, including method tsunamis, including volcanic sources, but of course dangerous crustal faults everywhere. And I thank you for your attention.
Thank you, Dr. Stefano Lorito. Thank you for detailed information about the warning systems and actions. I'm waiting for questions. We have a question to all speakers, but before from Dr. Dimitris Sakalariou, I wait the specific questions to Dr. Lorito first. After that, we will move to the general question by Sakalariou. Anybody has any question? I also check YouTube channel. Is there any question from YouTube channel? No. So there was very some coincidence with my presentation and Lorito's presentation, but his map was much larger than my map about the Aegean Sea covering west side, because there are other earthquakes in the west side of Aegean Sea and west of Greece. Those should be considered in the tsunami hazard assessment. And also multi-hazard assessment is important we should keep in mind. I would like to move Sakelario's question. His question is general to all speakers. He tells that in most cases we use seismic hazard in order to assess tsunami hazard for seismic sources, means fault, seafloor ruptures. But what about tsunami hazard from submarine landslides? The latter may occur as a result of an earthquake or may occur aseismically. How we can assess landslide triggered tsunamis? So, and also how we assess landslide triggered tsunami hazard. I don't know, Stefano, do you have any comment on this question?
Yes. What I thank Dr. Sakelario for the question. It's right. What we have shown is about tsunamis generated directly from earthquakes. So the system is triggered by the seismic shaking, the tsunami warning system. The hazard is calculated, as pointed out, starting from seismic source model, but the community is working on the integration and also getting to also landslide hazard modeling. There are several groups dealing with that. Maybe one difficulty is that treating the landslide hazard in a probabilistic way is more difficult, more challenging, and some details are given in the paper of Jörn Behrens and co-authors also, but there are already, to my knowledge, several scenarios of local impact that are being taken into consideration in this respect. For example, for Italy, from Professor Tinti's group, and now Filippo Zaniboni and Alberto Armigliano, for example.
Thank you, Stefano. I would like to add a few words from the Sea of Marmara. There were landslide features that happened in the past from the marine surveys in the Sea of Marmara. However, we are not certain, we don't have more information to estimate the size of the landslides. However, it has been included in our project for Istanbul Metropolitan Municipality. However, it needs more investigation, marine surveys, to understand the features better. So thanks for the question, because it is one of the other important sources of tsunamis, and it may happen unexpectedly. Thank you very much for the questions, and also thank you, Stefano Lorito, for your nice presentation. I'm going to move.
Thank you indeed.
Thank you. I'm going to move the next presentation. Presentation title is Development of Disaster Prevention Platform in Coastal Resilient Community. Presenter is Professor Dr. Taro Arikawa. Professor Arikawa is a faculty member in the Faculty of Science and Engineering in Cho University, Japan. He is an expert on coastal engineering, design of coastal structures, assessment, prevention, and mitigation of tsunami and storm surge disasters. He has long-term field experience. I mentioned that after Bodrum coastal earthquake, he came to Bodrum 2 times for survey and for a few hours presentation in the workshop in Bodrum. So he has long-term experience, experimental and numerical works on tsunami damage, especially on coastal protection structures. Professor Taro Arikawa, stage is yours. Thanks for your presentation in the beginning. Clear?
Can you hear me?
Okay, yes, we hear now.
Ah, okay, okay.
Can you-
Sorry.
Okay, screen is clear with your presentation and sound is clear, please.
Ah, okay, okay. Then the sound. All right. Thank you for invitation. And my presentation title is the development of the disaster prevention platform in coastal resident community. And my name is Taro Arikawa. This figure shows the situation at the shelter when the typhoon hit last year. And you can see here, sorry. Here is the status of the evacuation, and they were full. This is a Japanese character, but these are the full. These means full. So the many evacuation places are full because of coronavirus. And the Japanese government say that under the coronavirus, we avoid these 3 C's: the closed spaces, crowded places, and the close contact settings. So we are considering how to evacuate, how to proper evacuation places for the residents. And this is a history of the coastal protection policy in Japan. So the 1956, the Japan Sea Act Coast was established. And the government decided to protect by using the seawalls against the natural hazards such as the storm surge and tsunami. And the bottom figure shows the number of casualties of each tsunami and storm surge. So the 1896 Meiji Sanrik tsunami, maybe the 27,000 people will die. But after the Sea Coast Act was established, the not so large tsunami or not so large typhoon were not hit in Japan. But 2011, the huge tsunami was occurred. So I think we are changing the thinking about not only rely on the seawalls, but also the working together with urban designs. And maybe Professor Imamura said that the guidelines for the reconstruction. So that this is how to design the resident community against the natural hazards such as tsunamis and storm surge. So this is a concept of the resident community. We should protect against the high frequency tsunami. So the high frequency tsunami is lower than the largest class of tsunami. And in addition, we are considering the appropriate evacuation sites. So it is important to consider the evacuation plan. So we need not only the evacuation door, but also the proper direct directions to evacuation centers should be needed. So we are now developing the new platform against the coastal communities. So this is the concept of the new platform about this project, and this is for the platform. We are the platform working with the residents about the urban design. So we are developing the flooding database And the second one is the database for the laws and evacuation places. And the third one is a behavior, so human behavior for the evacuation. And the fourth one is how to for the countermeasure for the policymakers. So and also we are developing the smart evacuation guidance system for determining where and when to evacuate. That is by using the smartphone and the artificial intelligence. So these are the contents. I would like to say how to estimate the damage. This is the numerical models. And the second one is how to evacuate. So this is for the evacuation tools. And the last one is, I think it is not so many times. So I think that introduced the easily intelligence. And at first, how to estimate the damage. This is the numerical models to simulate the physical mechanisms. And now we are developing the multi-scale, multi-physics integrated calculator for storm surge and tsunami. And these are from the epicenter and to the structural destruction. And from the epicenter to the coastal line, we are using the nonlinear long wave equations to avoid to eliminate the calculation cost. And these simulator connected with Navier-Stokes simulations, and then finally these Navier-Stokes simulator connected with the structure analysis. And we also these are connected the multi-agent simulator for the evacuation modeling. And we are considering the validity of this model by using the Kamaishi breakwaters damage. This is the Kamaishi Bay after 2011. So these are the breakwaters. The depth of the breakwaters is 63 meters. So that is the deepest breakwaters in all over the world. And these are the almost 2 kilometers breakwaters are there, but half of the breakwaters were washed away by tsunamis. And this is the failure of the breakwaters. The snapshot, not snapshot, but the front view of the breakwaters. And these breakwaters, height of the breakwaters is almost 30 meters, but these were washed away almost 30 or 50 meters long. And the remaining breakwater was tilted. All of the remaining breakwater was tilted. And now we made the numerical input data from the epicenter, from nearby the epicenter to the breakwaters areas. And 1, 2, 3, 4, 5 is the nonlinear shallow water equation. And 6 is Navier-Stokes equations with the continuous water surface equations. And the 7 and 8 is Navier-Stokes equations, and the SDR is the structure analysis. So these are the coupling simulators, two-way coupling simulators. And we also making we also made the breakwaters, but this is without the slit part. And these are these breakwaters are analyzed by FEM analysis. And we can also set the properties for the caissons and rubber mount. And so it is very important to set the friction coefficient between the caisson and the rubber mount. And then in this case, static coefficient, static friction coefficient is 0.6 and dynamic friction coefficient is 0.4. And these are the incident wave and the incident input boundary. So the wave boundary in the east side of the numerical simulation, numerical domain, and the input data by using the observation data. And this is the whole animation of the numerical simulations. So eastern side, the waves is coming, and after coming the tsunami, then maybe you can see these structures are washed away. I think so. So at first the lava mound breakwaters were washed away, and the northern part of breakwater were washed away next. So this is the damage situation of the submerged breakwaters. So here is the image, not the results of the numerical simulations, how to damage the breakwater, submerged breakwaters. And at last, the damage of the breakwaters at the northern part. So the northern part of breakwater is very shallow in shallow region, so that the weight of the breakwaters are very light, so that the tsunami coming after as soon as tsunami coming, these breakwater was washed away. And after that, the deeper breakwaters were washed away. And this is the experimental study of the physical experimental study, how to damage, how to wash away. So yes, these are the breakwaters, and the tsunami were coming. Then the water difference between the front side and rear side, then these breakwaters were washed away. And duration time of the duration time of the damage and the washed away is very short, maybe 20 or 30 seconds in the realistic scale. Then how to support the evacuation. So now we are making the evacuation planning source. And this is the relation between the mortality rate and the rate of the height of the lake, the height of the lake, height of the seawalls. The horizontal axis shows the ratio of the tsunami height to the seawall height, and the vertical axis shows the mortality rate. So I think maybe you can understand of course the seawall height is higher than the mortality rate is lower. So you can see the 0.4, maybe like this. So the half of the seawalls, then the mortality rate is very high. So we need to develop the evacuation planning tools. And the arrival time, this is the relation between the arrival time and the ratio of the mortality rate. So of course the tsunami arrival time is earlier than the mortality rate is higher. But this is depend on the ratio between the evacuation start time to the tsunami arrival time. So maybe we need a system to support. Support evacuation. Support evacuation is very important. So now we are preparing for the coming smart city era. These are the outlook of the evacuation support system. So at first we are calculating the tsunami by using the many tsunami sources, and we developed the many database. Then after that, if the tsunami occur, then we choose from the tsunami database. We choose the proper inundated area from the database. Then by using these database, we are supporting the proper tsunami evacuation load. Yes. So this is a very detailed one. So I think how to avoid the tsunami encounters. So these are the tsunami encounter system, and I think this is very easy, but it is very difficult to make a program. This is a verification of the application of the field, application in the field. So this is Otsuchi town, I think so. The red color is the evacuation places, and the blue one is the evacuation load. So, and then by using the multi-agent simulations, we can verify and confirm the verification of this kind of system. And we are using the tsunami sources by the Tohoku earthquake tsunami. And this is if you choose the shortest route, if you choose the shortest route to the evacuation shelter, then the evacuees encounter the tsunami. So he was washed away or something like that. But if he choose another route by using this by using this tools application, then he choose another evacuation shelter, and he choose another evacuation road. Then he can be successful to reach the evacuation shelter. So this is the difference between the with or without the encounter system, the avoidance system. So this is the shortest route to the 2080s, but this is also the longer than the longer distance. But the evacuation places well to avoid the tsunami. So this is the difference between the mortality rate and evacuation start time. So the red one is the avoidance system, and the black one is the shortest time system. So these are maybe the maximum is 6.8, so almost 7% reduction to for the mortality rate. And the last one is the how to show by using the smartphone. So this is the device for the decision support system, and maybe we can select the evacuation road, but I think it is very difficult to choose the appropriate evacuation road, so that we are making the smartphone system by using the AR. And we expect the we are tested. We tested in the field area. This is a very straight line, but we are the testing by using this AR system. And this video shows that he selected the evacuation route by using the AR system, and he saw the smartphone and how to evacuate by using the smartphone by using this system. But this is very interesting. But from the residents on the older, elderly person, from the comments from the elderly person, it is not so good for the elderly person. So, but I think a younger person, they can adapt these kind of systems. And the last one is how to support against the other natural disasters. We also making the same evacuation system by using the valve or some typhoon system, and storm surge simulators. And we are also making the database, and we expect the predict the tsunami storm surge inundation and the storm surge the starting time. And by using these kind of system, we can also show the evacuation route. And also the heavy rain and storm surge, heavy rain and storm is also same. So now we are making the database of the flooding area by using by heavy rains. So after that, now we are making by using the artificial intelligence system. Then we take it eliminate the calculation time to show the appropriate evacuation route. Okay. This is our physical experiment. This is the videos, the physical experiment, like very small, but not like party, but this is very small. But the students are very interested in these kind of basement. Okay, thank you very much. Thank you for your attention, Sensei.
Thank you, Dr. Arikawa. Thank you, very nice presentation. It shows every aspect of the tsunamis. I would like to check, there is a question from chat from Yavuz Arda Çiçek. He thanks you, Dr. Arikawa. His name is Arda, coastal engineer, master student in METO in our department. He kindly asked thoughts about computational efficiency of solving 3D Navier-Stokes equations and volume of fluid method to capture free surface. Does it take too long to perform a large-scale simulation with your method, or did you optimize your code to work faster? And also, I might miss if you talked about do you use dynamic or static mesh? His questions. There are two questions.
Okay, yes, I understand. But now we are making the adaptive mesh method for the CAD stuff. So, but this is a very high calculation cost numerical simulations. So that I think this is not for the academic is very good, but the practical use, it is not so good for me. So good for us. So that now we are thinking how to eliminate the calculation cost. Thank you very much.
Thank you, Arikawa Sensei. We have a very limited time. I would like to summarize a few words from your speech with a question. Are your evacuations on foot evacuation or any vehicle is used? Because my question behind, there is a experience in Istanbul Metropolitan Municipality, because there is a traffic coordination commission in the metropolitan cities. We have to cooperate with them very much. Is there any similarity in your experience?
And this simulator is on foot, and we don't think the car or a bicycle, but I think this is a very important thing. So now we are considering how to treat the traffic jam or something like that. So this is maybe the next the future problem, but I think it can be done because Professor Imamura and other members are already making these kind of evacuation tools.
Thank you. Thank you. That's very good information for us to develop the evacuation maps for our country. So I would like to thank Dr. Arikawa Sensei very much for his very nice presentation. And
thank
also I would like to thank all participants for their questions and for their existence in the workshop. And we reflected Japanese experience and Italian experience to our participants. I thank all presenters and also finally Arikawa Sensei very much, Imamura Sensei very much, all Lorita and Basile also. I would like to close the session because at 10 minutes duration, a new session, poster session of young scientists will present their works shortly. So I would like to close session with my best wishes to all participants and also organizers, mainly Orhan Tatar and TÜBİTAK and 9 Eylül University and all other supporters, Cumhuriyet University from Turkey. Thank you, everybody.
Thank you very much, Professor Yalçıner, for your great efforts in sharing the session, tsunami session. So we will have a very short break and we will start the poster session at 11:50. So see you in 5 minutes. Thank you very much for their great efforts.
Thank you.
Okay,
bye.
See you.
Bye.
Yeah, bye, everyone.
You.
Ciao, adesso mi sentite? C'è il coffee break al convegno. Ognuno per conto suo. Io siccome il caffè l'ho preso prima perché adesso non so perché non mi sembra di aver premuto il pulsante, ma niente, quindi forse la sessione dopo magari mi metto lì ad origliare qualche cosa, però
Evet Derman Hocam, are you ready for the poster presentation?
Hi, Orhan Hocam.
Okay,
yes,
so we
ready.
can start maybe in 1 minute. So Savaş is ready, I guess.
Okay. Do you hear me? By the way?
Yes, yeah, that's great. Savaş is also ready, I guess.
Okay, can we start?
Yeah.
Or
First presentation. Yes, we can start now.
okay.
That's 11:50 now.
Yeah.
Can you hear me also? I'm Savaş.
Savaş, we can hear you nicely. Okay.
Thank you.
Dear participants, welcome to the poster session of the ASASE meeting. We have 5 poster presentations today. And as an information, all of the posters uploaded already onto the conference website in full-size PDF format, and you can check them if you wish. In the poster session, each contributor will give a short presentation with 2 slides consisting of their main results. The time will be a maximum of 5 minutes for each poster presentation. At the end of the poster session, after all of the presentations are completed, we will have a discussion session for 15 minutes, maybe a little bit more if we need, and it will be open for everyone. So you can direct your questions or comments during the discussion session using questions and answers button at the bottom of your screen. Okay, let's start with the first poster presentation. Its name is Submarine Stratigraphic and Structural Features Offshore of Küçük Menderes Graben, north of Samos Island and surroundings by high-resolution seismic reflection method, and will be given by Savaş Gülçay. Savaş, you have the floor. Please start your screen sharing.
Okay. Share it. I think it's going to start. Is it okay? Can you see the presentation?
Yes, we can see your presentation in presentation mode. You can continue.
Okay, thank you. I'll continue. The study area comprises the north of Samos Island and the offshore Küçük Menderes Graben and the Gulf of Kuşadası and Sığacık Bay. You can see the active faults on land here, and there are important 2 highs, 2 horse in the Seferihisar High and Karaburun High here, and 2 important peninsula, and the Teke and the Doğan Bay peninsulas. Here I'm continuing to the results. We use here the multi-channel seismic reflection data, and after the processing in the Dokuzeli University Marine Science and Technology Institute, we started to interpret the data, and the seismic section is there's 2 units, main units. Is the upper units is the positions, and the lower units is the in the basement. The upper units is consists of the stacked delta lobes, which the source of the Küçük Menderes River, and I correlated these stacked delta with the oxygen isotopic stages, and I gave the upper unit the age of the Pleistocene stages, and I'm continuing with the correlation again. Here is the you see how I did the correlation with the oxygen isotopic stages and sea level changes, and you can see here the upper units and stack delta and topset and foreset transitions, and the lobes represents the glacial times delta progradations, and you see here the acoustic temel is the acoustic basement, and the lobes, the different colors represents the different ages. This is the years in thousands,
and I'm continuing not keeping so long. And as you see, how I correlated the sea level changes and the stack delta progradations. And I continued to do this this correlation and the interpretation to all of the lines, and which intersection each other's and continues together. And as you see, the faults and the active faults and this seismic sequences on screen. And I'm continuing immediately. And this is the one of the seismic section and offshore Küçük Menderes graben. After the interpretation, the data, we can easily see that the offshore of the graben, Küçük Menderes graben, is continuing like this, and there's a graben shape offshore of the graben and on the land, and also you can see the normal faults here, how continue, how track the Küçük Menderes graben here. Now, then I modeled the Küçük Menderes graben here, and you can see the Küçük Menderes graben faults and the delta lobes and delta progradations here. And the faults here in S21 here is the south of the faults of the Küçük Menderes graben. And I'm continuing. I also, after the collecting data, we correlated the seismic sections in the milliseconds. We produced the map of acoustic basement and sediment thickness map, and we correlated with the active faults on land and the under the water, under the sea, and also continue as the results of the all of the interpretation and comparison of the data on land and under the sea. We produced these active tectonic maps. You can see the Samos earthquake here, location of the Samos earthquake here, and as a conclusion, as a result of the comparison with the oxygen isotopic stages, there are 13 delta progradation happened the places in glacial times, and the technical and structural interpretation were carried out to constitute submarine active tectonic map of the study area by correlated active faults identified on seismic sections, and the submarine active tectonic map based topography and the sediment thickness map were correlated together to present the relationship between tectonic deformation and stratigraphy. It was observed that the Küçük Menderes graben continues west and east northeast direction under the sea, and the normal faults limiting the south of this graben structure extend towards the Samos fault, as you can see on the active tectonic map here. And thank you for your listening.
Okay, so thank you for your quick presentation. We will have questions and comments in the end, if there are any. So we can continue with the next presentation, which is precursor analysis of 30 of October 2020 Samos earthquake using swarm A, B, and C magnetic data, and will be given by İlkin Özsöz. As I see, İlkin Özsöz is ready. İlkin, do you hear me?
Yeah, I'm ready.
Okay, can you share your screen, please?
Now I can't share my screen because Savaş should close the sharing.
Savaş, could you please stop your sharing?
Okay, I'm looking at that. Sorry for this.
No problem.
Just
stop share. Yes, here, I think.
Now you can see my screen?
Yes, we can.
Okay. Today I'm going to present precursor earthquake analysis of analysis by satellite magnetic data. Actually, we are not expecting this study as a poster presentation because it's a huge study for 5 minutes. Therefore, it will be extremely brief explanation of the study, and I'm sorry about this. First of all, this study is the 6th study in the literature that uses satellite magnetic data for precursor earthquake analysis.
There is a distortion in your microphone, I think.
You can't hear me? Can you?
No,
No.
I can. There was very high noise. Now it's okay.
Okay, I'm starting again. Today, I'm going to present precursor earthquake analysis by satellite magnetic data. Actually, I'm not expecting this study as a poster presentation because it's a huge study for 5 minutes, and therefore it will be extremely brief explanation of the study. First of all, I would like to say that this is the 6th study in the world that uses satellite magnetic data for precursor earthquake analysis. Now I'm quickly moving to the methodology part. Firstly, we obtained magnetic field components X, Y, Z, and F. Secondly, we removed external magnetic field effects from these components. This part is quite important because if we can't remove the external magnetic field properly, it will cause misinterpretation. Thirdly, we constrained our study area by Dobrovolsky zone. Then we take first time derivative of our data and remove long-term trend by spline interpolation. Finally, we obtained our first qualitative interpretation result for just a single satellite track. Now, in this figure, as you can see, this figure shows approximately 1 month ago from the earthquake, 22nd of September 2020. And in the left-hand side, there are magnetic components. In the right-hand side, there is our study area. And there's an anomalous zone indicated with red dashed circle in this figure. But it's just a single track analysis. In our study area, I don't know, we have maybe 200,000 satellite tracks, and we can't analyze all of them qualitatively. We need some autonomous and quantitative methods to analyze all tracks. Therefore, we used RMS window to detect all anomalous zones, and we plotted them cumulatively. I'm not going to talk about these results. I will directly move on to the interpretation part. And as you can see, I just want to interpret Y component of the magnetic field because the best result is obtained from the Y component of the magnetic field. In this figure, the vertical black line shows the date of the earthquake, and the pink line shows the polynomial fit to the data. And if you look broadly to the figure, you can see that there's an S-shaped anomaly. This S-shaped anomaly is quite compatible with previous 5 studies. And we can say that before earthquake, there's a linear trend. And just before the earthquake, there's a deviation from the linear trend. And after the earthquake, there's an exponential rise. Sorry, to conclude with, I can say that there's somewhat relationship between seismic activity and magnetic anomalies. However, there are only 6 studies about this subject. We need further studies to investigate and prove this relationship. Thank you for listening.
Thank you, Ilkin. We can continue with the next presentation. Ilkin, please stop sharing your screen.
Okay, if I find it. Yes.
Okay. The next presentation is nonlinear soil behavior analysis of collapsed building after the Samos earthquake, and will be given by Özkan Özdağ. Özkan, are you ready? Hear me? Do you hear me?
Yes, I hear you.
Please share your screen.
We sent a video for this presentation yesterday, but if there's a problem, I can open it here. Do you hear me?
Yes. Do you want to share a video with us right now?
Yes.
Murat Bey, is it possible to share a video with us? Orhan Hocam, Murat Bey, yes.
Buyurun hocam. Sesinizi alamadım hocam, buyurun.
Özkan Bey bizimle bir video paylaşmak istiyor şu an ama yapamadığını söylüyor. Mümkün mü?
Şu anda yetkili hocam, panelist yetkisi var. Özkan Cevdet Bey değil mi hocam?
Evet, doğrudur.
Evet.
Şu anda paylaşabilir. Bir engel yok hocam.
Kendisi paylaşabilir şu anda.
Evet, şehir yapabilir.
Görünüyor mu şu an?
Evet, şu anda gözüküyor hocam. Geldi.
Evet.
Tamam, teşekkürler. Sorry for Turkish. We are trying to share a video with Özkan, and yes, I think he can continue right now. Yes, Özkan, please go on.
Sesini açması lazım Cevdet.
Evet, şu an ses alamıyor.
Okay. Let's try this. Thanks, Mr. Chairman. I begin by sending greetings to all participants. I am Özkan Cevdet Özdağ, and I work for the Kuzey University Earthquake Research and Implementation Center. The issue I will present you today is which named the nonlinear soil behavior analysis of the collapsed building after the Samos earthquake. The reason for doing this research is that we are looking for the answer to the question of why the demolitions caused by Samos earthquake affecting Izmir occurred in the Bayraklı district, whose building stock is not different from the general of Izmir. And in this context, we started to work by creating soil bedrock models to make one-dimensional equivalent static earthquake log analysis in all buildings that collapsed after the earthquake. And in this context, I will share you one of the preliminary results of this study. In many studies, including our team in the past, the possible effects of the deep alluvial structure of Bornova Plain, which includes the Bayraklı district, on earthquakes have been investigated. As a result of this research, the basin geometry and general physical structure of the plain have been revealed. Unfortunately, after the Samos earthquake, destructions took place in the Bornova Plain, which confirms the results of these studies. Within the scope of this study, as you see, the earthquake data on the ground surface was transferred to the interface of bedrock by using the soil bedrock model of BY strong motion station located in the west of Bornova Plain. As you can see, north, south, and east-west components of accelegrams and location of strong motion station and collapsed building. The idealized soil profile for a building that collapsed afterward was prepared for the integration of HPSR inversions and microgravity models. One-dimensional analysis was performed with the prepared idealized soil profile. Vmax and PGA values of each layer interface were calculated that analysis by using the deep soil software. As a result of HPSR inversion, it was observed that the depth of the engineering bedrock was 230 meters approximately for collapsed building. If you want to examine obtained one-dimensional VS-depth models, low velocity zones with a depth of 35 to 65 meters are observed. And these velocity zones, low velocity zones, have potential to create a resonance effect between the soil layers. The soil models defined in the Pamuk et al. Study, it's seen that the seismic bedrock depth is in the range of 1,200 meters on average at a study area. By proportioning the ground surface to peak acceleration values of bedrock, the soil amplification value that occurred during the Samos earthquake on the ground surface was calculated. As a result of these calculations, the soil amplification for the collapsed building was calculated as 2.34. In addition, whether the deformations occurring in the soil under dynamic loads remain within the elastic limits or not was calculated with Ishihara's approach. According to the results of the calculations, the soil under the collapsed building showed a nonlinear behavior by exceeding Midorikawa's threshold level from a depth of 45 meters during the Samos earthquake. Finally, it is recommended to use detailed geological and geophysical soil models together to demonstrate these effects and make 2- and 3-dimensional soil analysis. Also, the structure designers should use in-situ design spectra from cross-sections on monoplane. For this reason, the ZF soil class given in Turkish earthquake code is highly recommended the study area in designs. Also, it wouldn't be a realistic mechanism to reduce the demolitions to only soil problems. It will be possible to avoid such distractions in the future with joint efforts of geology, geophysics, and earthquake engineering disciplines. Thank you all for your attention.
Okay, thank you very much, Özkan, for your nice presentation. Next one is the Samos earthquake of 30 of October 2020, and its aftershocks, and will be given by Dr. Mehmet Utku. Mehmet Hocam, are you ready for presentation? Mehmet Hocam, do you hear me? I see that he's here, but I think he cannot.
He's on the panelist list. He should be.
Oh, yes. Okay.
I read it.
Okay, Mehmet Hocam, can you start your sharing your screen?
Okay.
With us?
Okay. I start.
Not yet. I cannot see your presentation now. Did you press the share stream button, the green button at the bottom?
Okay. Can you see?
Okay, we can see the presentation. Please take it into the presentation mode, and that's it. Yes. Okay.
Okay. Thank you. We have discussed all together from yesterday about Samos earthquake 2020. The seismicity in the epicenter region has continued until today. The number of aftershocks are 5,913 events between 1 and 5.3 for 6 months. The map shows that the epicenter distribution of these. On this map, there are two important swarms. One of them is here, other is here, that's in the vicinity of the epicenter. Aftershock occurrence frequency has been showing orderly, decreasing response as exponential. At once, I must explain in here, in the study, it was used electronic earthquake catalog data recorded by Boğaziçi University, Candid Observatory, and Earthquake Research Institute. Here, this figure illustrates event number versus ordinal number of days and seismicity rate versus ordinal number of days. In the same way, an identical response is in use for this figure. Here, instantaneous energy rate versus ordinal number of events and energy rate per day versus ordinal number of days. If we make the vertical cross-section of hypocenters of these aftershocks, we obtain that image. From sequences of hypocenters in here, the slope is about 30 degrees. Orientation of the slope is towards to north direction, and also from aftershock duration analysis, aftershock duration for Samos earthquake has been estimated as maximum 3 years. Yes, as results, one, the Samos earthquake occurred in the eastern Aegean Sea. Two, the characteristic uniqueness of this earthquake is that even from offshore, it inflicted considerable damage to lives and properties in Izmir. Three, the main shock came from an east-west oriented deep slip normal fault with an north 30-degree slope. In the deformation zone, 5,913 earthquakes were recorded at greater than 1 within the subsequent 6 months. The highest magnitude of an aftershock was 5.3. The expected direction of earthquakes events is the maximum 3 years, 6 from the epicenter distribution, and the magnitude of aftershocks, it can be said that has not been occurred a specific asperity during the main shock because of aftershock occurrence process. Thank you for your attention.
Thank you very much, Mehmet Hocam, for your presentation.
Thank you.
The last presentation is paleoseismic history of Manisa Fault Zone, Western Anatolia, and will be given by İsmail Duran. I think İsmail is here. Mehmet Hocam, could you please stop your screen sharing?
Murat Bey, duyuyor musunuz bizi?
Mehmet Hocam.
Mehmet Hoca ekran paylaşımını unuttu sanıyorum. Bunu biz alabilir miyiz, o yetkiyi kendisi?
Alalım.
Alalım hemen. Mehmet Utku'nun ekran paylaşımını alıyoruz.
Aldık hocam.
Tamam.
Kahve arası falan mıdır, değil midir?
Tamam, şu anda diğer son konuşmaya başlayabiliriz.
Değil mi? Tamam.
Tamam. İsmail, can you start sharing of your screen?
Okay. Hello everyone.
Okay, we can see your presentation. You can start now.
Hello everyone. Today I will tell you about the study area is located in the Western Anatolia region, where the extensional tectonic regime is dominant, and also within İzmir-Balıkesir transfer zone. The main motivation for this study is that paleoseismology-based trench studies were carried out in the west of the study area, but a detailed study was not carried out in the segments located to the east of the Manisa Fault. Within the scope of this study, active fault mapping studies were carried out on the eastern segment of the Manisa Fault, which is included in the active fault classification. In the light of the data obtained, 5 paleoseismologic area were determined in the most suitable places stratigraphically. The basement rock units in the study area consist of the late Cretaceous, Borneo-Philistone, Miocene volcanic and sedimentary rocks, and quaternary units. Trench locations were determined were the Holocene deposits. In the kinematic measurements we made in the city center of the Manisa and its vicinity, we can mention that there is an approximately north and south extension, and the presence of northeast and southwest extension as we go east. Paleoseismology. In the Şahinkaya Trench, faulting has occurred after the deposition of G unit and I units and J units. It is seen that all events are limited by the current storage unit K. The faults observed in the trench were measured as the northeast dip direction. In the Şahindere 2 trench, faulting has occurred after the deposition C and D unit and F units. It is seen that all events are limited by the current storage unit I. The faults observed in the trench were measured as the northeast and northwest dip direction. It was observed Yarıkkaya Trench. It was observed that 5 events in the Yarıkkaya Trench. Faulting has occurred after the deposition of C units and D units and F units. It is seen that all events are limited by the current storage unit I. The faults observed in the trench were measured as the northeast and northwest dip direction. Kırtık Trench. In the Kırtık Trench, faulting has occurred after the deposition of B, D, and H units. it is seen that all events are limited by current storage unit I. The faults observed in the trench were measured of the northeast direction. Anıt trench. Faulting has occurred after the deposition E1, E2, and G0 units. It is seen that all events are limited by current unit H. The faults observed the trench were measured as the dominantly northeast deep direction. Seismotectonics and Oxcal date age. When the events determined from 5 paleoseismic trench site carried out in the middle and east sections of the Manisa Fault are evaluated together, it was determined that the fault has been the source of 6 earthquakes. One first event, second event, third event, and 5 events in this earthquakes. Thank you for everyone.
Okay, Ismail, thank you for your presentation. Now the presentation of the posters is now completed, and we can proceed to the discussion section. Please direct your questions or comments to the contributors using questions and answers button at the bottom of your Zoom screen. Then I will read them for the contributors. I'm checking the chat window and question and answer window if there are any questions or comments. No?
Chairman, may I ask Spiros Pavlidis?
Yes, you can.
To Ismail. Ismail, congratulations, it's a great work. But it isn't clear if you correlate some of your paleoseismological events with historical earthquakes, like that of AD 17. Do you? Ismail, do you?
İsmail, duyuyor musun Spiros'u sorusunu?
Or Hasan may answer this question if he is there. Hasan Sözbilir. Can
Yes.
you hear us?
Hasan Hocam, are you there?
Yes, I am here.
Can you answer the Spiros questions?
Yes, it's a great war with 6 at least events, but it is not clear if you correlate 1 or 2 events with the historical earthquakes, and how do you correlate?
You see the last slide here?
Yes.
Yes, here is the correlation.
Yeah.
As you see, one number ID 17 and in August 926 and in 1845 and in 1662. These are the historical earthquakes that we encountered within the trenches.
Okay, this is interesting.
Okay, can I ask a question, Derman?
Yes, sure, Orhan Hocam, please go on.
Well, my question to Savaş, but Spiros and also our other Greek friends may also answer this question. You know, after the Samos earthquake, we have experienced two many small to moderate size earthquakes in the area, occurred and still occurring close to Kuşadası Bay in the sea and also on land, falling mostly on the faults which are antithetic to Samos faults or the continuation of the faults coming from, extending from the Küçük Menderes Graben. So almost also 2 days ago, we have two small size earthquakes with the magnitudes of 4.2, 4.4 in the area where I live. In fact, my summer house around the Turkish coast and facing to, I don't know, Samos. So people living in the area are quite suspicious about the future earthquakes in the area because they are thinking that the activation of the Samos fault has triggered the other faults in land or also in the sea around the Kuşadası Bay. So do you think the activation of Samos fault in October 2002 has triggered the faults to the north or northeast in the sea or on land, the Turkish side? Can we expect an earthquake in the near future in the area?
Okay. Could you please answer the question?
Yes, I can start the answering. Now, by the way, can I share my slide also here to explain something?
I think you can. Please try sharing your screen.
Okay. Okay, I will explain. I'm sharing here. I will start with the final slide here, and as you see the location of the Samos earthquake in 2020, and if we look at the active section, active faults here, especially under the sea, and we can see the normal faults continues to the Küçük Menderes Graben and to the Samos Island, and this is the south part of the graben. I expect generally the future earthquake to the Küçük Menderes Graben, towards the Küçük Menderes Graben, or to the Samos Island. But also it can be also possible to occur in some earthquakes north part of the normal faults, and I mean the Turkish parts, as you see, if you can see the number of the faults here, and the S20s, S90s here, you can see, and there is a continuation to the west here. Also, in my opinion, it can be if we're talking about the Turkish part, and we can wait the important earthquakes around here also. But I'm suspicious about this direction to the Küçük Menderes Graben and to the north of the Samos Islands and to the Caribbean Basin. Also, this is the normal faults, and if there's a north-south direction openings, it can be also affect the north parts of the strike slip faults under the sea and on land also, as we know in a couple of days we saw that as the Orhan Tatar mentioned, some earthquakes. We can see also depending on the opening of this Küçük Menderes Graben here, we can see some faults maybe on north of this area also. Is there any question for this, or?
I do agree with you, because the stress transfer techniques, you know, they show either to the east or to the west that the active faults you'll show, and the extension to the Küçük Menderes as well. Mm-hmm. And the offshore of west of Samos, north of Ikaria, that faults of northeast southwest with oblique slips, right slip component. This can be a two candidates area for a future earthquakes, but who knows? On the other hand, we have the phenomenon of domino for long distances that it is not clear yet. You know, there is evidence for the earthquake of Athens of September 1999 that it followed the Kuchali the strong earthquakes. Possibly it is a domino in the area. And you know, in the last 3 years, we have in Bodrum, Kos, Lesbos, Samos, and now in the central Greece. That is not clear in the long distances, but in the short distance, you are correct. All these active normal faults, and both offshore and on land as well, they are candidates.
Okay, can I add something? I don't know if there is a stress distribution calculation in this area after the Samos earthquake.
Yes, there is.
There is, okay.
Yes, many.
Oh, okay, that's very important because
in the afternoon, one of my colleagues, it will show one, but some other colleagues, they applied the method of stress transfer.
Sure, great, that's great because the area is very active by means of east-west directional and north-east, north to south directional faults. I also agree with Savaş to see that if any stress distribution, stress accumulation on the Tuzla fault, I mean the Orhanlı fault to the north, which is very active in the offshore part, as I know from the Savaş data. So it's also an important fault for this area, and we have to check if there is something about the stress accumulation about over the Tuzla fault also.
Yeah, it's true.
Derman, you may answer maybe. You know, the Gümüldür fault is about 15 kilometers on land. And I think the last two earthquakes 2 days ago falls into this Gümüldür fault. Do you think the Gümüldür fault extends into the Kuşadası Bay, offshore to Kuşadası Bay for about another 15 kilometers, in total about 30 kilometers?
Orhan Hocam, I understand your question. It's a very nice question, actually. As Savaş showed several seismic lines in this area we collected in the past years. No, Savaş, don't change the slide.
Okay, sorry. The same slide. Do you want this?
That's okay. So, as Savaş plotted the faults in the Selçuk Bay or Seferihisar Bay, the faults here in almost east to west direction and not north to south direction. Actually, we collected very high resolution data very close to the land area in this bay using our Sparker data set, but we do not see a clear continuation of that fault into the offshore area. I don't know why. In the Kuşadası, in the Selçuk or Seferihisar Bay, the faults are normal faults actually, or maybe most of them are sedimentary faults, not related to the tectonism of the area. But anyway, they show the normal fault characteristics, but we do not see the continuation of that fault towards the south. But anyway, we see the continuation of the Tuzla fault to the south is very prominent in the marine side, but not the fault you mentioned, Orhan Hocam. I don't know why. You have to check it.
May I add something about this, about Kuşadası Bay?
Yes.
Okay, I just want to show that this section also, especially I want to talk about the Gümüldür fault. this direction is extends to the fold, and Gümülder faults is approximately perpendicularly, it's continues like that here, and you can see the normal fault starts offshore Kuşadası, not so much close to the shore, but I think this part faults, normal faults, this parts and S19, S20 are the same faults with the Gümülder faults, because these are the normals, and their tilting and deeping are the same, like the continuation, like the Gümülder fault, and it represents the opening of the Küçük Menderes Graben. I just wanted to add something like that.
Okay, thank you so much for the clarification. Is there any other questions or comments about the presentation of the posters? I am checking the YouTube site, and I also see there is no more questions or comments. So I think the presentation of the posters is now completed, and we can proceed to the lunch now. I thank you all contributors and participants. The meeting will continue at 2 o'clock in the afternoon. I also would like to thank the organizing committee, and especially to Professor Orhan Tatar for this nice meeting. See you in the afternoon after the lunch. I give the floor to the Professor Orhan Tatar now.
Okay, Derman, thank you very much for sharing the poster presentations. And yes, as you said, we will start the geodesy and active tectonics session in the afternoon. So we will see you at 2 o'clock. Bye-bye.
Bye, thank you.
Hi, Dr. Stramondo. Are you there? Dr. Salvatore Stramondo, you hear me?
Yes, yes,
That's
it's me.
So we will start soon.
Okay. Thank you.
Okay, so let's start the afternoon session. Good morning, good afternoon, everybody. Welcome to the Active Tectonics and Geodesy session in the second day of the workshop. Professor Sözbüller is working on the final declaration of the workshop together with Spiros and Ricardo, so I will chair this session instead of him. We have 5 presentations in the first part of the Active Tectonics and Geodesy session today. So I would like to thank to all the speakers for their great contributions. So the first talk is titled Co-seismic deformation field retrieval from satellite SAR interferometry for offshore nearby coastline earthquakes, hints from recent case studies in the Eastern Aegean Sea, and will be presented by Dr. Salvatore Stramondo. The floor is yours, Dr. Stramondo.
Thank you very much. Thank you very much. I try to share the screen. Okay. Can you confirm
yes,
you see the slides?
That's perfect.
Okay. So thank you very much for introduction and for this time. I would use to give some hints for discussion about the use of SAR interferometry in particular case studies that are those where the epicenter of the shock is offshore, nearby coastline, nearby island or islets, with particular emphasis on the Eastern Aegean Sea case studies. Few words about the overview. I will spend some slides about the SAR interferometry technique that is a well-known data processing technique based on the exploitation of synthetic aperture radar data and the DIN-SAR, differential SAR interferometry. Going on, I will give some hints about the seismotectonic of the Eastern Aegean Sea. Then, few points about the way INSAR works in some specific case studies that we will discuss. Okay, let's go on. As you know, today we are about 30 years after the first application of INSAR technique that was basically in the early 90s of the last century, 1992, in particular for the earthquake studies, so the Landers earthquake. But today, about 30 years later, INSAR can be considered an effective tool in earth sciences domain. Is a tool for scientists to investigate the surface effects of earthquakes, but also in many other fields of natural hazards. INSAR is a comprehensive technique for studying small to medium scale earthquakes, but also mega earthquakes. And today, following the first 10 years, 15 years, today we have a lot of data, a different band, XCL, at medium to high resolution data, and above all, a lot of satellite orbiting. So let's start with the first question. Does INSAR provide a reliable contribution to the retrieval of seismic fault parameters in case of earthquakes that are offshore, occurring offshore and nearby, of course, emerged lengths, but in particular when they occurs close to islands, small islands, etc. Which are the possible limitations of INSAR? Some of these are general limitations. We can talk about spatial temporal decorrelation, but this is a general problem. Another issue is the, let me say, the low magnitude effects at the surface and the deep hypocenters that hamper the surface expression of earthquakes. And finally, another intrinsic drawback, of course, you can say, of course, it doesn't work offshore, so water is not coherent. Few words about SAR interferometry. The basic concept is we can acquire, take a picture before a shock, before an earthquake, another picture after an earthquake, then we combine the phase component of the post and the pre-earthquake image in order to measure the surface displacement due to the earthquake. We cannot forget that the phase contribution content of INSAR is not in principle the displacement, but is the topography, the atmospheric phase, and other issues, as you can see. But if we remove topography, atmosphere, etc., and if we have a deformation occurring at the surface, it is an effective tool to highlight and to enhance, let me say, such movements with a very, very high accuracy. Today, this picture, I hope, explains well the situation. We have a lot of satellite missions and a lot also of satellite SAR constellation. So many data, so a lot of data, different bands, different site angle, and above all, this huge amount of data allow significantly reducing the temporal span between two or more SAR images. So I said that INSAR is able to measure coseismic displacement at different scales of earthquake. Just a few examples from the past. Landers 1992 and Italy 1997. 3 meters average displacement, 25 centimeter vertical displacement. But above all, as you can see, the scale is quite different. And the scale is so different in 2011. You know the mega earthquake hitting the island, the Japan, but Honshu Island in particular. You see in the picture the overall displacement due to the main shock, magnitude 9.0, and in the small picture, an aftershock that was not a small aftershock. It was a 7.0 magnitude aftershock. So INSAR, okay, another picture to show the big picture. INSAR is able to detect with the same accuracy, independently on the spatial scale, the surface displacement. I would close this part of the presentation with a reminder concerning this work from Dawson and Tregoning. That is a methodological work studying the trade-off magnitude depth and the detectability of the effects of such earthquakes. So, looking at the Aegean Sea, but more in general to the Eastern Mediterranean, in the INSAR era, let me say, in the last 25 years, a lot of shocks occurred in this part of the Mediterranean. We will focus on two of these. the 2017 Kos earthquake and the 2020 Samos earthquakes. But before looking and before focusing on the Eastern Aegean Sea, on these two main earthquakes, I would make a step to the west and to another case studies in 2014 that is a well-known earthquake hitting Cephalonia Island, and where we applied this, let me say, this concept. We were studying an earthquake in an island, occurring in an island, or to better say, two shocks, a 6.1 and a 6.0 shocks, and some hints that I'm going to point out have been applied in Samos and in Kos. Okay, let's start with the analysis of these Cephalonia earthquakes. So we are close to the Cephalonia transfer fault. We used RADARSAT-2, TerraSAR-X, and Cosmos Skymed SAR images. This means high resolution images, C and X band images from ascending and descending path. So we have in 2014 a lot of data, but RADARSAT-2 temporal baseline was very, very high, about 2 years and more. And this affected the retrieval, the possibility to retrieve the displacement field in the Paliki Peninsula, as this picture shows. Only some fragmented fringes have been detected. We then, while on the contrary, TerraSAR-X and Cosmos Skymed, mainly thanks to the very short temporal baseline, were able to describe much better the displacement field. We use also permanent and non-permanent GPS stations in order to invert with a simple Okada model, so with many limitations, elastic half space and a uniform slip on the fault plane, the displacement field. And the result was two faults, a deeper one and a shallower one, that describes the overall picture from SAR and GPS. In this slide, Cosmos Skymed and TerraSAR-X have been used to point out and to invert the second shock effects at the surface. So also in this case, INSAR provided an effective contribution to understand what was going on in 2014. So some points to close and to introduce the other two case studies. We had the 3 SAR dataset, co-seismic field not only partially retrieved on land, because a part of it was missed due to the sea, a simple Okada model. So the idea was to study the overall picture and not to go to the spatial unhomogeneities of the field, of the displacement field. INSAR fringes, in particular for RADARSAT-2, were sparse due to the correlation. INSAR, in any case, provided a robust constraint to the fault geometry retrieval. Okay, let's move to the east. We are in the Aegean, in the Eastern Aegean Sea. Very simplified geotectonic map with the subduction of the African plate and the Hellenic arch, as you can see from the picture. Samos earthquake. The yellow star is indicated the epicenter. We are in an area known as the Western Anatolian Extension Province, so characterized by a normal, an extensional regime. Samos occurred, the magnitude 7.0, occurred in a region not new to these strong earthquakes, you know, and you can see in this very simple picture. And the earthquake caused a lot of damage in the area from around the island and in the island of Samos. So some studies have been carried on, and the idea was to apply a multidisciplinary approach to understand the geometry and the parameters of the fault using GNSS data, seismological data, and INSAR data in order to obtain a progressively reliable, let me say, model, thanks to the additional data that were acquired in the days, in the hours following the shock. The first data were Sentinel-1 from ascending and descending path, and these data were processed using a common platform that is GEP, Geohazard Exploitation Platform from the European Space Agency, and applying 3 different approaches. Later on, the early post-seismic, the coseismic with the early post-seismic displacement have been measured thanks to the use of the Gamma software applied to the data repository, the Sentinel-1 data repository. And these are the results. I would put the attention in this other picture on the B profile that cut from northeast to southwest Samos, and that shows the usual, the well-known trend of a coseismic normal fault expected at the surface. This data, together with the GPS displacement, horizontal displacement vectors, in particular Samo, allowed to generate, using a simplified Okada model, also in this case, a number of models that progressively increased the accuracy. Just to start, the first model, INSAR plus GNSS, highlighted the southwest dipping of the fault, while from the Model 2 to the Model 4, adding GNSS refined solutions, seismological data, and in particular the Samo GPS data, strongly preferred the north dipping of the fault. So in this case, INSAR was not able to discriminate, to give a contribution to discriminate between south or north dipping fault. On the contrary, in the case of Coles Bodrum 2017, also in this case, we are in the Aegean Sea, 6.6 moment magnitude. Also in this case, the authors of different papers use the coseismic simplified models, so an Okada formulation, applied to GNSS and INSAR data. But in this case, GNSS, although was able to define well some model parameters, didn't allow to discriminate between the south and the north, or the north dipping of the fault. The seismology and the seismotectonic was helpful from this point of view, of course, because the knowledge of the seismotectonic of the area gave, let me say, a confirm about the dipping of the fault. But let's start with the approach used from different authors. The combined use of geodetic data first, so coseismic INSAR and GNSS offset, the relocation of seismic data, and other informations, ancillary informations. GNSS vectors have been used to infer the fault parameters, INSAR in particular to define, to contribute to the dip. This is a very first interferogram that was generated a few days after the earthquake. But it is very interesting. This is from the ESA, European Space Agency news web page. It's interesting to see that the displacement field, it is a 6.6 earthquake, seems to be concentrated on the Cara Ade Islet, that is the land close to the yellow star. Much less on Kos, something, but it might be also atmosphere in the area of Bodrum to the north. And this is the GPS vectors retrieved, measured in the coseismic, due to the coseismic effects of the earthquake. Concerning INSAR, in the days, in the weeks following post-Bodrum earthquake, the European Space Agency made available Sentinel-1A and 1B TOPS images with a very short spatial baselines, and this is a very, very important parameter to reduce the decorrelation, the spatial decorrelation. And these data were combined in order to highlight the fringe pattern and in the inset, the absolute displacement on Cara Ade, in particular, Cara Ade Island. You can see some centimeter displacement. This is confirmed from other authors, other works, that this is only an abrupt interference, so you only see the fringes, but the concept is, let me say, exactly the same. INSAR data have been inverted using a simplified Okada formulation, also in this case, the Okada formulation with a simplified analysis of the seismic source provide a really a strong instrument to understand which is the geometry, let me say, and the deep of the fault. But you see on the left the inversion of the ascending Sentinel-1 interference, and on the right the descending orbit. You see also the modeled and the measured GPS vectors in the region. You see the possible fault dimension, the black rectangle. As I anticipated in the first part of this the description of post-Bodrum earthquake, GPS could not discriminate exactly between north and south dipping fault. And in fact, in the upper right part of the slide, you see the best fitting fault model using only GNSS data. This information, useful for other constraints, has been supported from INSAR that allow to obtain a best fitting fault model with some uncertainties, of course, but this fault model clearly, let me say, demonstrates that is preferable the north dipping fault. So a strong contribution in this case from INSAR. I'm going to
last 3 minutes, Dr.
I'm going
Samos.
to thank you very much. I'm going to conclude in any case. Okay, so post-Bodrum, progressive accuracy, also in this case for the model. First one, use of GNSS only, does not discriminate south or north dipping, while from model 2, GNSS plus ascending and descending Sentinel-1 interference. Okay, I already showed the results. So what we can say in this case, that INSAR strongly supports this the analysis of post-Bodrum fault retrieval, although part of the displacement field cannot be fully detected, but the use of ascending and descending view provided two different lines of sight that in any case were very, very useful to achieve this result. So the question, the first question, does INSAR provide a reliable contribution to our case studies? In principle, the answer seems to be yes. Going deeper in the analysis, we can add that INSAR is a comprehensive tool that provides a big picture of the investigated area with a lot of information, because a lot of pixels, a lot of data are in the interference, and each of them is a contribution to understanding the situation. So we can say that in particular, the actual situation today's, the actual availability, strong, big, large availability of INSAR data is a reliable tool to overcome most of possible drawbacks that the sparse SAR data acquisition in the early 90s gave as a limitation for the application of such technique. So this is my last slide. Thank you for attention. And please, if you have questions, I am available. Thank you.
Okay, thank you very much, Dr. Stramondo. I don't see any question on the Q&A and chat section of the Zoom application and also in the YouTube channel. Maybe one short question, if you have any question from the panelists list. Otherwise, I will just move on to the next presentation now. Thank you very much, Dr. Stramondo.
Thank you very much.
Okay, the next talk will be given by Alexandros Chassipetros and his friend, Dr. Lazos. The title of the presentation is "How can geodetic data help identify regional and local crustal deformation patterns, examples from the broader Aegean area?" Okay, the floor is yours, Alex.
Thank you, but the previous speaker has to stop sharing his screen so that I can share mine.
Oh yeah, just stop the screen, Dr. Stramondo.
Okay.
That's fine, okay.
Just a moment, please.
Okay.
Okay. So this presentation is about use of primary geodetic data for the identification of some local deformation patterns. And I would like to present you some results from which come mainly from my PhD student Ilias Lazos' work, and concern these issues. First, let me say a few things about what our thinking is. I mean, we know since several years that GPS data and GPS information show very reliably the displacement pattern for the broader area of whichever study area we are dealing with. For example, we are well aware of the counterclockwise movement of Anatolia and the change in direction. You see here a compilation map of several authors for Eastern Mediterranean, and also from several studies for the Aegean area. So this general pattern is well established, and we know that this is the case. But sometimes we need to look more carefully into specific areas. For example, in this map, you can see some smaller displacements due to the movement of the part north of the North Anatolian Fault, which, however, cannot be analyzed in detail and give us specific results. So in this work, we try to dig into the data and find information, at least about straying parameters that can describe the actual the ongoing actual deformation, not always expressed as displacement, but it can be expressed as deformation. For this, we used a time series of a continuous time series of for 7 years, using data from 159 permanent GPS stations. You can see here the distribution of those stations in the mainly in Greece, but also in some stations in the neighboring areas. And I will come back later to this map at the end of my presentation. Several networks, we used information and data from several networks, and we tried to solve the data using the ETRF 2000 reference frame. So what we did is that we used those data from 7 years, 2008 to 2014, and these were continuous time series, meaning that they were time series covering 24-hour operation of the stations, and all the measurements were taken every 30 seconds. So you can see that this is a very big, a huge amount of information, of data. For each station and for each specific measurements, the model, the information that we got from the model was the velocities, north and east velocities in the two axes, north south and east west, the vertical velocity, and the component errors for each one of those velocities. To use these measurements, we discarded the vertical velocity because you know that vertical velocity is not very well expressed in GPS and measurements. So we worked with east and north velocity together with their error margins. In order to process the data, we used a quite simple methodology, which I would like to explain to you briefly. This methodology is a triangulation of sites and a triangulation of respective measurements. It all starts with 3 neighboring stations and the corresponding east and north velocity vectors, from which then we can calculate the total horizontal velocity, which is the component of those 2 vectors. So for each site, we can have this kind of configuration with the horizontal velocities that are produced by this process. The next step is to find the center of this triangle, and this is why it's called triangulation, which we consider that it represents the status of the entire area within this triangle. So for this, the centroid, we can we draw a circle with the center of which is the centroid of the triangle, and then based on the vectors, on the component vectors, we move the center of this circle, and we move the triangle corners accordingly to the vectors. This is an automated procedure which leads to the deformation of the circle. This deformation shows us, the axis of this deformation shows us the main deformation pattern in the area. If we then translate this to this ellipse to the initial position of the centroid, we have the final product, which is the centroid of the deformed triangle and the ellipse that shows the actual deformation pattern in this point. So This can, of course, be automated, but it needs a lot of attention from the user and some critical reviewing, because one has to be very careful about choosing those three triangles and applying, at least what we did is that we applied geological data, geological information, so that we can have triangles that have a meaningful geological, that show a meaningful geological situation and active tectonic situation. That is, triangles that probably are belonging to the same block, or that have some faults crossing the areas, etc. And this is the final product, these two axes. And of course, any structural geologist can understand that if the difference between those two axes is large, then the deformation pattern in each in that point is large. If the difference between those two axes is small, then there is not much deformation. So by using, let me go on, by using this data and combining the information, we estimated some parameters for the specific point, which is, again, by definition, it is representative of the area between the three stations. And by using those parameters, we interpolated missing values through kriging. So what were the parameters that we extracted from this process? Mainly the maximum and minimum horizontal extension. I'm going to use these letters later on, so to save some space. The total velocity of this point, the maximum shear stress, and the area strain. And I will explain to you later what each one of these means. Apart from these parameters, a few more were extracted during this process, but they are not relevant, or at least they are not very useful at this presentation. So I'm going to show you two examples, one from Central Greece, the Corinth Reef system, and one from Northern Aegean. They both are two very different geotectonic environments. Corinth Reef system is a well-known complex graben system with normal faults bounding both of bordering the Gulf from both sides. So in this area, we used information from 14 permanent stations, and the resulting calculations were done by using 26 different triangles between those stations, as well as different centroids, 26 different centroids. So what is, let me just start by the maximum horizontal extension. These are the results of this analysis, and it shows that there is a difference in various parts of the Gulf. They are consistent with this general map. This is by Hollenstein et al. 2008, which also shows an anomaly in Corinth Gulf. However, this analysis shows this deformation in more detail. Maximum horizontal extension is equivalent to the maximum extensional axis if we are talking with structural terms. And again, we see that these, if this is the quantitative information, these two areas show more extension. They are more, let's say, active areas in respect to the others, although one could argue that all faults in this area are active. Again, the next parameter is the total velocity. Again, we see here a pattern that is consistent with the known models, but one can see that values north of Corinth Gulf are generally smaller than the ones south of the Gulf. This is consistent with the general geologic situation in Peloponnese, which is this area here, where the geological observations show that extensional deformation is much stronger by exposing lower tectonic units. Again, the quantitative results, which are not very important at this point. However, the maximum shear strain shows a quite interesting result. These are the areas of the centroids with the maximum shear strain in various areas. Those three are consistent with the maximum extension that I showed you before. However, there is one area here that is not represented in any map. You see here, this is the the part of GREDA, the grid database of seismogenic sources, and there is no fault in this area. The reason that this area shows such a large shear strain is because in 2008 a strong earthquake happened and caused the deformation of this area, despite no fault reaches the surface. Up to then, there was no fault, no known fault that reached the surface. Again, the same, the area strain is consistent with the maximum extension in these areas, but also you see here the area strain that corresponds to this event. Let's move on to the conclusions for Corinth Gulf before we move to the next area. There is this shows a differentiation, a local differentiation of values. Some of them, most of them are consistent with the general model. However, if you dig into the data, you can see that there are some smaller areas of specific interest, and especially the 2008 event is completely changing the overview of the area. And another example from North Aegean, which is well-known area. This has some interesting features. The main is that it is mostly covered by sea, so the distribution of stations is not very good. Again, with the available data, there were 32 permanent stations and 404 centroids, again, using the triangulation method. And this shows, again, some interesting results. I'm going to go through a bit quickly because time's running out. The maximum and minimum horizontal extension, as you can see from the magnitude of the arrows, in most cases is consistent with a known structural pattern. However, there are some areas like this area in Thrace where the deformation of there is a large deformation without having any large known active faults. And the total velocity again shows quite interesting result. The area south of the North Anatolian fault is as expected, moving with larger velocities. However, there is significant movement again from north to south in northern Aegean, and there is an area north of the North Anatolian fault where there is again southwestward movement with all the uncertainties because this is the sea. The same again with maximum shear stress. It is concentrated in some well-known areas that we expected to have a maximum, to have a shear strain. And again, there are some areas like here in Thrace or in central Greece where the shear strain is larger than expected, and probably due to local local tectonic conditions. The same goes for area strain. Again, the same results for the large structures of the area, and again some localized areas that are undergoing deformation without any visible any large large known active fault zones. And let's close this section with a few conclusions. That it is the main deformation type is shearing, because we know that it is associated with cyclic folding. However, in some points we have, as mentioned, pure dilatation. So to conclude, if we take the bigger picture, and this is these are the results for the entire area, we can see that there are various parameters shown in areas of well-established fault zones, but there are also some local, let's say, islands of deformation in areas with no large faults or small faults that we did not expect. So the same goes for shear strain and area strain. So we think that this can be a good way to have an indication of ongoing deformation in areas outside the main zones. But one problem here is that this was a, let's say, a test run of 7 years. We need longer time series, but more importantly, we need information from more stations, especially from Turkey, so that we can have more reliable results for the entire area. And one idea is to have this automated so that we can establish a continuous monitoring system that can show active deformation in real time. So thank you for your attention.
Okay, thank you very much, Dr. Chatzipatsos. I also thank you for using the virtual background of the workshop behind yourself. Thank you very much. So we have time for a few questions. I don't see any question on the chat or Q&A section of the Zoom application, but if you wish, we can have some short questions among the panelists, if they have. Okay, I think no question. Alex, thank you very much again for your great talk.
Thank you.
Would you please, okay, stop your screen sharing. And the next talk is prepared a group of researchers from different universities of Turkey. And the title of the presentation is GPS-derived finite source mechanism of the 30th October 2020 Samos earthquake, MW 6.1. So the talk will be given by Professor Bahadur Aktu. The floor is yours, Professor Aktu.
Thank you very much. Okay. Today, I'm going to talk about the finite source mechanism solution of the Samos earthquake. Okay. All right. We're going to talk about the earthquake in October the 30th, but in general, we are experiencing many offshore earthquakes in Aegean Sea. Geodetic measurements are not very sensitive to far-field deformation, so it's generally a technical challenge to get some coseismic deformation and to process and analyze. these co-seismic observations. For one thing, inside observations are generally partly available and sometimes not available at all. And GNSS observations, the network in offshore, near the coastlines are not sufficient to provide sufficient constrained parameter space. So we started just a re-survey of the available network just after the earthquake in 1 week. And after that, in this observation schema, we collected 62 sites, and we obtained 62 sites co-seismic offsets. And after that, we modeled the co-seismic offsets for both uniform and distributed slips. Our uniform slip model shows a finite source of 43 kilometer long and 16 kilometer wide rupture, which slips 1.42 meter on average. We're going to talk about that later. And that rectangular finite fault lies back down to 13 kilometer depth. And we also observed some close sites to the epicenter were not able to be modeled, sufficiently. So we provide the distributed fault model, which provides a nearly perfect fit to the observed surface displacements. You'll see some the area of interest at different zoom levels, and the fault lines and the delineations, let's say, come from different sources in the literature, about 20 different sources. The offshore delineations are mostly based on seismic profiles, and also in the length, some faults are obtained from active fault map and many other literature studies. In the right, upper right and lower right figures, you will notice that the available fault delineations does not necessarily coincide with the result geometry, which is about which lies in northeastern and northwestern and southeastern direction. And in the lower right figure, you will see some historical earthquakes in black asterisks, mainly from the 19th century. And this is the sort mechanism from different centers, and we also included our solution in this table. Our GPS solution is the first one here, and tips are more or less similar. In solutions, it's about 45 degrees, and strike is also seems to be our solution is a bit. It's compatible in general, but it's usually 20 degrees tilted from the east-west direction. And GPS is these are all point sources. These are all come from seismic solutions. These are all seismic centers, and this is finite solution, so there's no auxiliary plane here. So the latitude and the longitude corresponds to the centroid of our rectangular fault, and this is strike. And yeah, it is mostly normal faulting with a little bit lateral component. And this is the depth of the lower edge of our rectangular fault. And this figure also shows the aftershocks. This is the big Menderes graben. It is the largest graben in Turkey with an extension rate of about 6 millimeters per year. And since this is graben and the obtained solutions is a normal faulting mechanism, it gives the impression that these donations should be compatible with this one in length, or the fault traces just in the northern part of Samos Island is just westward continuation of this Menderes graben. And these are the sites we used for collecting observations. We have both continuous and campaign type sites, and quartz TR, which is a national continuous GNSS infrastructure, let's say. And Turkish National Fundamental GPS Network, this is not a continuous network, but it is the first order network of Turkey, providing very precise, both good stable monumentation and historical record. It goes back to 1997. And these are just simple sample pictures. And these are the observations. And total, we have total 62 sites, 29 campaign sites and 33 continuous sites. All the campaign sites were observed at least 8 hours with 30-second sampling interval. And all the observations took place between 5 and 8 November. So it is just in 1 week. So we don't let post-seismic deformation go on or interfere with our observations. And all the GNSS data were collected and processed with comet Globk software with the state-of-the-art models. All right, this is a figure for my continuous site. I mean, Izmir and Mantesh sites in the Karaburun Peninsula. And for continuous observations, we have more epochs before and after earthquake. And instead of differencing the closest epochs here to get the co-seismic displacement, we divided our domain, the time part, in pre and post parts, and we averaged both the pre and post parts to minimize the noise and increase the precision for all three components. This is east and this is up. And this is the first order picture of the observed and modeled displacements. As you see, there's the closest sites in Samos Islands are not modeled very well. On the other hand, the far field sites, these areas are a little big, so actually this side and this side, they are about 100 kilometers. So it just constrains the attenuation of the model, which is directly sensitive with the length and the general mechanism of the fault. We use the elastostatic green functions, Okada 1985, and we don't allow any tensile component, no opening, so only strike slip and deep slip were allowed for the inversion process. We downweighted the vertical offsets about 1/3 of the original uncertainties, which corresponds to about 10 times variance downweighting. And for the optimization, we use a hybrid approach, which employs simulated annealing, which can avoid the local minima. And afterwards, we used an efficient algorithm, BFGS, it is derivative-based method. The objective function is the weighted residual sum of squares. So we employed the full covariance structure of the observations. In this two-step approach, we first inverted the fault geometry, keeping the slips on the faults constant, actually just 1 meter. And after that, we modeled the slips. And this plot shows the trade-off of the parameters. Actually, each dot here, it's an experiment consisting of 100 different experiments. And each dot here actually corresponds to one experiment, one inversion. And using the original coordinates matrix, their error estimates, we produced 100 different observation data set and inverted them one by one to examine the trade-off between parameters. Here, the moment is not an independent parameter since the slip is fixed. It's an auxiliary parameter here. All right. And this is our distributed fault model. As you can see, even the closed sites are modeled very well. There seems to be an observation error at this point. Otherwise, it provides a very decent fit, let's say. We use the modified Lancaster inverse scheme for the distributed slip model. This step is completely linear but ill-conditioned, as you know. So we constrained our model with some roughness constraint, and we used the steepest descent minimization method to get the slip at each patch. These are the patches. As you see, in general, the slip is concentrated in the western part of the fault, and all the slip is really limited to the 12 kilometers, first 12 kilometers, and at larger than 1 meter slips are limited to a 7.5 kilometer step. These are in different three-dimensional perspectives. All right. In accordance with the north-south extension tectonics of the Aegean region and coseismic displacement calculated from the geodetic data also confirm a pure north-south extension, just very small, like that was also obtained during the inversion. But we can say that it's pure north and south extension. It's a north dipping fault, by the way. And the largest movement caused by the October 13th, 2020 Samos earthquakes. The magnitude is also discussed after every earthquake in Turkey. Our geodetic inversion shows a moment magnitude of 6.9, and the largest movement was observed at Samos station, and it is the closest station to the epicenter of the earthquake. And similar results were obtained in the studies, in some of them about earlier reference cited in the previous slides presentations. And the largest coseismic displacement is 136 millimeter at the north component, since it's a north-south normal faulting. And yes, our strike is 288 degrees, which is consistent with the findings of other researchers and also consistent with other seismological centers. The coseismic inversion of dense GPN area in the study reveals a finite source of 43 kilometer length fault, and which is close to the estimate of ALIAS et al. 2021 of 37 kilometers, but it's 1/2 of 80 and 100 kilometers given by Doğan et al. Our estimated width of the fault in uniform model is 16 kilometers. This uniform slip modeling is very useful for it provides a comparable outcome of the results. All right, and okay, but we also show that a uniform slip model is not enough to account for all the observed displacements in the field, so a distributed slip model is needed, at least for our study. If it weren't for TÜBİTAK, we wouldn't be able to carry out these observations, so we would like to thank TÜBİTAK for the rapid financial support just after the earthquake. And also, this project was supported by Afyonkarahisar University Scientific Research Foundation and also TÜBİTAK. We already said that. And we would like to particularly acknowledge the data for this study. These are the continuous sites to Turkish COSTIR, Turkish national continuous GPS sites, and private Greek networks, SmartNet, and for providing the data. And also, we'd like to thank many individuals who took part in the field observations. Mainly, these are students at both undergraduate and graduate level. Thank you for your patience and interest.
Okay, thank you very much, Professor Aktu. So we have time for discussion or any questions. We have completed earlier than scheduled program. Any question you can ask also live from the panelist list. I can't see any question from the Q&A section or chat section, but we have time, and I can see a question for Alexandros Chassipetros for the earlier talk. Are you there, Alex?
Yes, I'm here, but I did not have any questions. Sorry.
Well, you can also read from the YouTube channel, but I can read it. That was asked by Roberto Basili. A question for you. when you say that in an area there is no known fault, do you mean lack of studies or lack of data?
Okay, what I mean is that there are no known, not well established active faults. I mean, there are fault zones which are not characterized as active or possibly active. So in these cases, we believe that these are either indications of activity for older faults or some very local disturbances in the stress regime, in the strain pattern, due to maybe a block rotation or something like that.
Oran, may I add something?
Okay, please do that.
The example from Northwest Peloponnese in 2008, that the seismic event that you have seen from the presentation of Chatzipetros, I was only an example in my presentation that it was a blind fault, an unknown strike slip fault. So it appeared from the nearest, the geometry of the surrounding faults, and we understood that the geometry shows that it was a strike slip fault, a blind fault. In the same area, Alexandros has shown the results of the GPS.
Okay, thank you, Spiros, for your contribution. Any more question? I think no. So I thank you both, Alex and Bahadur. So we can move the next presentations that will be prepared by Spiridon Mavroulis and his friends. And the title of the presentation is Field Observations and Insar Analysis for Mapping Environmental Effects Induced by the October 30, 2020 MW 7.0 Samos Eastern Aegean Sea Greece earthquake. Okay, the floor is yours, Spiridon.
Good afternoon, everyone. Just a minute to share my screen.
Okay, that's perfect.
Nice. I'm going to present you the field observations and INSAR analysis for mapping environmental effects induced by the Samos earthquake in the earthquake-affected Samos Island. This is a collaboration of the Department of Geology and Geoenvironment of the National and Kapodistrian University of Athens and the Earth Observation Team of the Charokopio University of Athens in Greece. The Samos earthquake was the largest event in Europe and Turkey in 2020 and the most lethal worldwide due to its fatalities. And its epicenter was located offshore northern Samos. The applied methodology included field surveys in October and post-event field surveys in October and November 2020 and in January 2021 after an aftershock of MW 4.7. Moreover, we compiled a relevant questionnaire and disseminated to the local population through social media and along with the support of the local authorities in order to detect more earthquake environmental effects. Initial analysis and as well as application of the environmental seismic intensity scale for the detected primary and secondary environmental effects. The geological structure of Samos is composed of four tectonometamorphic units, which are the following from the base to top. The Kerketeas unit in the western part of Samos, which is considered to be the relatively autochthonous unit of the island. It comprises marbles and schist on top. The Abelos nape, which also comprises mainly schist and marbles. The Seljuk nape in the southern part of Samos, including metabasites. The Vourliotes nape in the eastern part of Samos with schist and marbles. The Calithea nape in the western part with sandstones, peridotites, spilites, and fossiliferous limestones of Ammonitic Rosso type. The geological structure of Samos also includes recent formation of Neogene and Quaternary age, which filled in the Karlovasi Basin in the western part of Samos, the Mytilini Basin in the eastern part, the Paleoprikos Basin, and the Pyrgos Basin. As regards the active faults of the island, the most active ones are the Karlovasi Fault, the Vathi Fault, Pythagorio Fault, and Marathokavos in the southwestern part of the island, as well as the major offshore fault in north of the Samos Island. Based on the aforementioned methodology, we detect the primary and mapped primary earthquake environmental effects, including permanent surface deformation with uplift, permanent seismic uplift in several sites around the island, and moreover, seismic surface ruptures generated mainly in the northwestern, northeastern, southeastern, and southwestern parts of the Samos Island. The first site with detected uplift was in the Karlovasi vessel shelter, where the uplift reached 24 centimeters and was imprinted in the dock of the Karlovasi vessel shelter. West of the Karlovasi shelter, we have two more sites with generated uplift at the Akra and Punta promontories. The uplift in Akra promontory was 20 centimeters, and in Punta promontory was about 22 centimeters. And in both sites, the uplift was imprinted on Kerketeas marbles. The next site was in Agios Nikolaos in northern Samos. We detected two phases of uplift. The uplift attributed to the main shock of October 2020, and the uplift of due to the aftershock of the January 2021. The first one was about range from 15 to 20 centimeters. While the uplift attributed to the aftershock was about 8 to 10 centimeters. The next sites, uplifted sites, were Marathokavos and Kambos in the southwestern part of Samos. The uplift from the main shock attributed to the main shock was about range from 15 to 20 centimeters, and due to the aftershock, ranged from 8 to 10 centimeters in both sides. Similar uplift values were observed in the southeastern part of Samos in Pythagorean Psylli Amos areas, and ranged from 15 to 20 centimeters. Another one site located west of Pythagorio site were detected at the Potokaki area. The uplift in this site ranged from 17 to 25 centimeters. Moreover, in the northeastern part of Samos, uplift was also detected in the rocky beach of Asprochorti, and it was about 10 centimeters. Moreover, except of the coseismic uplift, we also observed the coseismic surface ruptures in Agios Nikolaos and Agios Ilias areas in northern Samos. In Agios Nikolaos, they constitute an almost 1 kilometer long zone. Their strike varies from north 40 to north 70, while their vertical offset range from 5 to 8 centimeters. Based on the kinematic detected in the field, we concluded that the northwestern rupture block was subsided, while the southeastern rupture block was uplifted. Similar characteristics were mapped in Agios Ilias area with 600-meter long coseismic surface ruptures with similar strike and vertical offset, as well as the subsided and similar subsided and uplifted blocks. North-south of the Agios Nikolaos of the previous sites in Agios Nikolaos and the Agios Ilias sites, we also observed coseismic surface ruptures in the area between Brises and Kotakeika villages. The surface rupture zone has a length of about 1 kilometer with a northeast-southwest strike and deep to northwestwards. Their vertical offset range from 5 to 10 centimeters, and subsided. The northwestern block was subsided, while the southeastern rupture block was uplifted. More surface rupture were observed in fields south of Brises village, with similar strike, deep, vertical offset, and width. Moreover, the earthquake of Samos induced secondary environmental effects, including slope failures, hydrological anomalies, liquefaction phenomena, ground cracks, and coastal areas affected by tsunami. Slope failures were observed in the northwestern part of Samos, along the Karlovasi-Kalithea fault. The first site was observed along a fault scarp in this coastal area. It has a height of more than 40 meters, and the marble are strongly folded, resulting in their disintegration into small fragments or their decomposition into powder. During the main shock, unstable blocks of marble were detached from the upper parts of the slope without impact on the adjacent coastal road. Slope failures were also observed in another rockfall site along the same fault. Similar detachment of marble fragments occurred in this location along the Karlovasi-Kalithea fault. Rockfalls and landslides were also observed in the northeastern part of Samos, in the southern coastal part of Vathi Bay. They were triggered in Kedros, Kokari, Lemonakia, and Avlakia sites in this line. The largest effects were generated at the Avlakia site, resulting in temporary traffic disruption in the northern part of the island. Due to the reactivation of these landslides due to aftershocks, a barrier made of large concrete blocks was created along the base of the slope in order to protect the road and passengers from the continuous landslide activity. Kokari was another one coastal area affected by slopes and rockfalls. Rockfalls were observed in the landforms of the affected area, in its peninsula and the islet, as well as the coastal part of the city. The landslides, the rockfalls occurred along the slopes of the Kokari Peninsula, resulted in non-structural damage to the adjacent reinforced concrete building and partial destruction of a wall at the base of the slope. More slope movements were observed in the southeastern part of Samos, in Remataki rockfall, in Remataki area, and in the marina of Samos. They were attributed to differential erosion of the formation along these slopes. The underlying marls eroded and were easily eroded than the overlying limestones, resulting in excavations and subsequently rockfalls of the limestone blocks. Similar phenomena were observed in this slope of the marina of Samos, composed of travertine limestones and marls with intercalations of clay. Rockfalls were also observed in the central and southern part of Samos, in Platanos area, Kumeika village and Tsopela Cape. As regards the liquefaction phenomena, they were observed in the coastal area of Malagari at the southern Vathi Bay, an area composed of alluvial deposits and sands. And these photos are from the Maunes beach located northwest of Malagari port. And they comprise typical phenomena, including an extensive network of cracks in the ground, ejection of liquefied material composed of water and sand, ground subsidence at the part of the beach, as well as lateral spreading of the coast towards the sea. Ground cracks were also observed in coastal areas in Malagari and Petalides in the northern and in the southeast, in the northeastern and northern part of the Samos, respectively. And they were attributed to unstable conditions of the artificial deposit used during the construction of the coastal roads. The secondary earthquake environmental effects include also hydrological anomalies in several sites of Samos. They were observed in the eastern part of Kerketeas, in Abelos area in the northern part of Samos, in the central part of the island, and in Mytilini Basin at the location of Kazania. They included changes in the flow rate of water springs and the reappearance of springs with increased water flow. As regards the deformation field visualized by the interferometry analysis, the deformation field, the displacement maps are similar qualitatively in terms of the direction of the displacement uplift in the central and the northwestern part of the island and downlift along the coastal area. The displacement maps are very close quantitatively, showing an uplift of up to 13 centimeters along the line of sight, and a downlift of up to minus 12 centimeters in the line of sight for the ascending data, and 9 centimeters and minus 14 centimeters in the line of sight, respectively, for the descending interferometric pair. The up, down, and east-west displacement composition results show that in the vertical displacement, the positive values mean upward to 13 centimeters, and the negative values downward up to minus 14 centimeters, respectively. For the horizontal displacement map, positive values mean eastward up to 8 centimeters, and negative values westward up to minus 12 centimeters. From the comparison of the vertical displacements derived from the two softwares used in INSAR analysis, it is concluded that the results seems to agree in general, having a deviation of up to 2 centimeters. Horizontal deviations, however, are larger, especially in areas with high topography, which were not completely removed in the case of the SNAP software. From the comparison of our field measurements and the INSAR analysis results, it is concluded that all studied sites and areas, the results from both methods are qualitatively identical but quantitatively different, except with the exception of Asprochordi and Kokari areas in the northeastern part of Samos, where there is neither a qualitative nor a quantitative correlation. Based on the special distribution of the earthquake environmental effects, we applied the environmental seismic intensity scale on Samos Island. Based on this application, it is concluded that the maximum intensity is 9 was assigned to sites affected by seismic uplift larger than 10. Intensities 8 to 9 were assigned to sites with smaller amounts of uplift induced by the January 2021 aftershock of magnitude 4.5 in southwestern Samos, and also to sites with coseismic surface ruptures in the northern part of the affected island. Intensities 8 were assigned to sites affected by surface ruptures with a length of several hundred meters, in landslides with large volumes of mobilized materials, and to the extensive liquefaction phenomena. Sites affected by slope failures were characterized by intensities varied from 4 to 8 intensity. 6 to 8 intensities were assigned to sites affected by liquefaction phenomena, and 6 and 7 intensities were assigned to ground cracks and to springs suffered by hydrological anomalies. In conclusion, the primary earthquake environmental effects detected in the field comprise surface deformation, including permanent coseismic uplift and coseismic surface ruptures, mainly in the northern part of Samos. The secondary environmental effects were also generated mainly in the northern part of the island and include slope failures, liquefaction phenomena, ground cracks, and hydrological anomalies, as well as ground cracks due to local failure of coastal road embankments. With the contribution of the INSAR analysis, subsidence was also detected at coastal areas in Ablakya area, and slope movements identified in inaccessible areas of the Kerketeas mountain in the western part of Samos. Moreover, the type of deformation of the surface deformation detected in INSAR analysis is qualitatively identical to field observations. As regards the special distribution of the primary and secondary effects, it is concluded that were generated in all fault blocks of Samos Island. Based on the guidelines of the ESI scale, the maximum intensities were observed in northern Samos. Taking into account the special distribution of the earthquake environmental effects and their mapping based on the post-event field surveys and INSAR analysis, it is suggested that the northern and northwestern Samos constitute an almost coastal Samos constitute an almost 30-kilometer long coseismic deformation zone with extensive primary and secondary effects. The surface projection of the coasative offshore northern Samos fault points to this extensive surface deformation zone, indicating a depth surface connection and revealing a significant role in the rupture propagation and the effects distribution. Thank you very much.
Okay, thank you very much, Dr. Mavrolis, for your very interesting talk. So we have more time to discuss, and if you have any question among the attendees or the panelists, we can have some questions lively if you wish. And going almost 15 minutes before the scheduled time. I don't see any question on the Q&A section or also in the chat section. So thank you very much, Dr.
Thank you for the invitation and congratulations on the workshop.
Okay, thanks for joining us. So we can now move on to the next and also final talk of this session, which was prepared by Sotiris Sporas and his friends. And the title of the presentation is Source Modeling and Stress Transfer Scenarios of the October 30, 2020 Samos Earthquake Seismotectonic Implications. So that will be presented by Dr. Sporas. Yes, the floor is yours, Dr. Sporas.
Sorry, but
Alex, you were present as well. Okay, that's great. Okay, sorry about that.
No problem. But the lead author was not due to a last-minute problem, he could not attend. So he asked me to present.
Okay, that's fine.
Sorry about that. But anyway, I hope I can present it in an adequate way. So this presentation is will give you some information about our model, about the source and the stress transfer scenarios of the Samos earthquake. It is relevant to the two previous talks, but we have some differences, and it is very interesting to have this exchange of ideas and information. So this is a cooperation between the Department of Geology at the University of Thessaloniki, together with our colleagues at the Hellenic Survey of Geology, as well as the School of Rural and Surveying Engineering, who helped us with the geodetic information. I'm going to go through quite not very detailed with the first few images, because we have discussed them extensively during these 2 days. This subduction of the African plate beneath the Eurasian plate, as well as the westward movement of Anatolia, causes the formation of a very complex geodynamic regime. This is a scheme by Taimas et al. 2007, which is generalized, let's say, deformation pattern of the area. Of course, there are some individual and local variations, but I think this map shows the distribution of deformation in a good enough way. The study area is somewhere between these boundaries. So as I will show you later on, this plays an important role in the nature of earthquakes, as well as the structural manifestation. This map, I showed it also in my previous presentation, but it shows the various types of crustal deformation using the GPS/GNSS data. And there are zones of intense deformation and zones of less intense deformation. And I'm going to go through these. So we have a very diverse faulting environment with faults of various types in the area, and this is a good. They are in good agreement with the focal mechanisms of the main shocks. You can see here some the red focal mechanisms correspond to thrust faults, to reverse faulting earthquakes, the blue ones to strike slip, and the black ones to normal faults. Although there are some, let's say, clear areas of distinct faulting, there are some areas that the style of faulting is mixed, as for example, in southeastern Aegean and western Greece, etc. And this is due the complexity of the general geodynamic complexity. This is a map with the epicenters for the period since 1964. Of course, we are all familiar with images like that, and a very intense distribution of seismicity in the area. Now let's focus in the study area of Samos earthquake. The data, historical and instrumental data, show that the area is not very, let's say, quiet from the earthquake point of view. There are a lot of strong earthquakes, Some of them are estimated, of course, for the especially for the older earthquakes. However, the seismicity here can produce earthquakes of magnitude 7 or even larger. So this October 30th earthquake is indeed one of the largest in the area, but it is not uncommon for the area. As mentioned before, the area is characterized by both strike slip and normal slip faults, as shown by the various focal mechanisms here. They are from Kiraji and Louvery 2003, and this is due to the concurrent operation of strike slip and normal faults in the area. Some faults, this area has this peculiarity that some faults are well documented in the mainland. However, some are not so well documented because they are located offshore, and their location can only be identified by seafloor morphology, earthquake epicenter distribution, and seismic profiling wherever available. If we look at the seismic sequence of the Samos earthquake, we can see that the epicenters are more or less located in an almost east-west direction, and this is in a good agreement with the distribution and the location of the Kaistrios fault, which has been described in previous studies, and is included in the Greek database of seismogenic sources. So there are the focal mechanisms, especially from the main shock and most of the aftershocks, show that these are they are in agreement with an east-west, almost east-west fault. However, there are some other mechanisms that are consistent with strike slip faulting of different orientation. So let's see some the distribution in space and time of the epicenters. During the first day, 13 October, the main distribution was around this fault. This is the main shock, and the first cluster started to develop towards the east. However, there is a distant cluster here, which is evident since the first day. By moving on to the next days, we can see that these clusters, the second cluster, starts to build up more activity, and the third cluster is starting to form in this area. I have to say that this distribution is the first distribution. They are not relocated epicenters, and I will compare these maps to the relocated epicenters in the next slide. Moving on in time, we see that these clusters start to get the activity is continuous in these clusters. However, a few days after the earthquake, there is another cluster, a D cluster, which is developed quite away from the main, from those three main clusters. So there are a few questions here, especially regarding clusters B and D. The main question is which fault produced them, because they are not. I think it is clear that they were not produced by the main seismogenic fault. If we compare these maps with the maps published by Cetin et al. 2020, with the relocated epicenters, there is quite a good agreement with the first cluster west of the main shock, the second cluster southeast of the main shock, and the cluster here north of Ikaria Island, with another cluster which, however, is not very well defined near the coast of Turkey. So as far as the surface effects are concerned, they have been presented by the previous speaker as well as yesterday by Galanakis and collaborators. This map is the neotectonic map of Samos with just the faults. This has been compiled by Montrakis collaborators several years ago. And the surface effects are shown in this map, mainly concentrated to the north coast. However, as we saw in previous presentations, there are also some features, some effects in the southern shore. One of the most interesting effects is the ground ruptures in this area in northwestern Samos. They seem to be secondary because they are located along mountain slope. However, they are very consistent in their strike, and they produced mainly opening, but also some vertical displacement. And this northeast-southwest strike is something that I'm going to come back again later. This strike here is consistent with the strike of this fault by Montrakis and collaborators, which is not very clear onshore, but we believe that it is associated with Ikaria fault to the southwest. So our model is somewhat different from what previous speakers suggested. We selected this fault because its source here, because we think it is in good agreement with a mapped fault, which is this one that is included in the Greek database of seismogenic sources, but also it is in good agreement with the distribution of most of the aftershock sequence. So we propose that this is a almost east-west structure of about 40 kilometers long, and it is also in good agreement with the Kandili Observatory focal mechanism. And also it is, again, in good agreement with the measured and the actual displacement, especially in Samos station. So this is a comparison between the actual GPS measured displacements as with the modeled displacement. We use the Okada model, as previous authors did as well. Of course, it has its limitations because it has the Okada model suggests that there is an elastic hull space and uniform slip, which we cannot be certain. However, they are in very good agreement, Samos and Ikaria stations. This model comes in good agreement. So we think that our proposed source model is confident enough. And you can see the comparison between the GPS displacement values and the model displacement values. In most cases, they are very similar. So based on this source model, we tried to calculate the globe static stress chains on the fault during the in sequence, as well as off the fault post-sequence activity. These are the distributions of the Kandili Observatory catalog. They are not relocated. They are, however, we use them because they have there are a lot of them, and we can have a first approximation of the distribution of seismicity in the stress drop and stress rise areas. So in each of the figures that I'm going to show you, we have a longitudinal cross-section and cross-sections perpendicular to the fault. So these three sections show the distribution of earthquake activity, of aftershock activity, and they are not, you see here that they are not very well defined in respect to the model fault. However, most of them are located in the stress drop area due to the stress release of the main slip, of the main shock. If we use the relocated hypocenters, we see here that the distribution is much is a lot better. They are concentrated around the model fault, and again we see here those two clusters that are at least problematic, or they pose some questions, and I'm going to discuss them later. Another cluster here, cluster C, is located away from the main fault, and it is again poses a question if it is produced by a fault or by another fault of different geometry and kinematics. This cluster C is not was not very clear in the previous distribution, but it is clear in the relocated distribution. So, for checking in and trying to find out which faults produced the different clusters apart from the main fault, we used all those faults around here. They are modeled faults in GREDAS, Greek Database of Seismogenic Sources, with their parameters, and we used each of them for as a receiver fault of the stress released during after the main shock. So just a quick overview. In each of those maps, you see that different faults have been taken into account in order to see in the cross sections if they correspond to stress drop or stress rise, and if we can possibly correlate them with the distant clusters. So the main issue here, the main thing here is that this fault, which is the Karlova-Sifurni fault, shows a stress increase in its upper part, which is in good agreement with the second cluster, cluster B. So we believe that the second cluster was produced due to the reactivation of this fault. And another possibility was the Ikaria fault, which is here. However, the cross section here shows that the stress rise is very low in respect to the Karlova-Sifurni fault. So this is a more probable source of activity. The cluster A, which is located here, is between those the main shock and the cluster B, can probably be associated with a transitional zone between those two faults, and they are in good agreement with the ground ruptures that I showed you in the previous map. The rest of the faults that have been modeled, the receiver faults, do not show any significant stress drop or stress rise. So they are differently affected, but they do not show any indications of post-sequence activation, post-sequence activity. So to conclude, the main some of the main conclusions, we see that the aftershock distribution shows development of different clusters, and we believe that those clusters were formed due to the reactivation of adjacent faults due to the stress drop or stress rise from the main fault. The ruptures that were observed, they are generally they are scattered, except the northeast southwest striking ruptures in northeast northwestern coast, which are consistent with the of a model of transitional structures between the two main faults, the east-west main fault and the adjacent Karlova-Sifuni fault. Another important point is that the GPS recordings show a very large displacement of 37 centimeters, which was quite surprising, and much less displacement in other stations. However, this is consistent with the model that we propose, and the proposed fault is along the northern Samos coastline. It is we propose an east-west structure dipping to the north, and this is consistent with the modeling, again, with of course with its limitations, with Okada displacement models, and the GPS measurements, the GPS values, they are all in agreement with the proposed fault. So we found also some distribution of stress changes, both stress rise and stress drop in various faults. And as I said, the different clusters appear to be produced by transfer of stress into adjacent faults, either on stress drop areas or on stress rise. This is, we think that both regimes can produce those clusters. So these were also the conclusions from this proposed model, and thank you again for your attention.
Okay, thank you very much, Alex, for this very important presentation that also answered all the questions in the earlier sessions. We have time, and we may have some questions or contributions from the attendees or the panelists. And I don't see any question on the Q&A section and also on the YouTube channel. Any question? I think I understand everyone is getting tired, so this is the last working hours of Friday, so I may have a bit longer break this time, coffee break, tea break. So let's meet at 5 minutes before the scheduled time. So 4:15, please. Okay, see you in 25 minutes. Okay, bye-bye.
See you later.
Thank you. Hi, Onur.
Hello.
You ready, I guess?
Yes.
Okay, so we will start in a minute. Hi, Ricardo.
Hi, you are free to use.
Getting tired. Very, very intense program. Thanks for the photograph, by the way. Okay. That was a big surprise.
Make the use you want.
Okay. Onur, how long will your presentation take? Just 20, 25 minutes, Onur?
Okay, I try.
Okay, so if you plan to speak longer, then we can start now, if you wish.
Okay, we can start if everybody is ready.
Yes, so we have now 4 minutes to go. So I will introduce in a minute. Okay, so let's start the final session of the workshop today, and the session is promoted to geodesy and active tectonics, and we have 4 different presentations in this session, and the first talk will be given by Dr. Onur Tan and his Greek friends. And the title of the presentation is Seismotectonic Implications of Karaburun Peninsula, Kuşadası Gulf, and Samos Islands. The floor is yours, Onur.
Okay, thank you. Firstly, I want to thank the organizing committee and also to Professor Orhan Tatar, who invited me to this talk. And I try to summarize our previous studies on Karaburun Peninsula, Kuşadası Gulf, and Samos Island. First, I try to talk about seismological data used in these studies, and then Karaburun Peninsula, Kuşadası Gulf, and Samos Island seismotectonics. I try to summarize them, and finally, I give some our recent findings about the recent Samos earthquake. This is the general seismotectonic map of the region, and I think there is no need to talk about this, but it's clear that our lives are controlled by the interaction among these 4 tectonic plates: Africa, Arabia, Eurasia, and also Anatolia, in means of the natural hazards. This plate interactions generates very complex crustal deformation, as you know. So we see all types of faults in the region. And not only in Turkey, but in the mainland of Greece and Aegean Sea, there are high number of small earthquakes and also large earthquakes with different physical properties. The study results that I show in this presentation is mainly based on our previous project when I was in TÜBİTAK Marmara Research Center. The TÜRDEP project between 2006 and 2014 is one of the comprehensive project with contribution of several universities and former structure of the AFAD. approximately 100 seismological stations and also high number of GPS stations, radon gas stations, and spring water stations were deployed 3 different tectonically different areas in Turkey. But unfortunately, only seismological stations are in operation today by AFAD. The other observation sites were removed several years ago after end of the project. In this project, the more than 30 seismological stations are in the Aegean region of Turkey and let us the high quality micro-earthquake observation in the study period. First, I want to thank to the project staff, and most of them are not at the TÜBİTAK Marmara Research Center at this time. The data in this presentation are from the TÜRDE project and also from our previous Turkish-Greek common project with my colleague from University of Thessaloniki. If you look at the microseismicity of the region, they are observed between the 2007 and 2012. There are more than 10,000 events in this period occurred in the region, and the earthquake clusters are clearly seen in the area with the high quality seismological observation. And we can see the different clusters, earthquake clusters in the region. An example in the İzmir Bay and Karaburun Peninsula and Kuşadası Gulf and the Kuşadası land area, and also Samos Island. On the other hand, there are also some silent areas in Gediz and Büyük Menderes Grebens. In this period, we observe very small number of earthquakes in these Grebens. If you look at our catalog pattern for this area, and the B value is the 1, approximate 1, and the complete magnitude is 1.4. This is a good value for a seismological observation in Turkey. And if you look at the located events according to the origin hours, the smaller events, smaller than the complete magnitude events, we can less earthquakes in the daytimes according to the night times. This is actually caused by the high ambient noise in the day hours. On the other hand, the earthquakes larger than the 1.4 are uniformly occurred all hours in a day. After located the earthquakes, all of the phase peakings are reading manually. After the absolute locations of the events, we try to improve the locations using the waveform similarity. Here is an example. There are 2 events between 100 seconds. There are 3 components records here. The upper is the earthquake 1, the other is the earthquake 2. If you notice that the P waves or S waves and the wave shapes in the tail of the seismograms are very, very similar. That the absolute locations of these 2 events are very close, and the waveform similarity indicate that the both are occurred on the same fault surface. This is another example. We can use the similarity to improve the focal locations using the double difference inversion, as I mentioned before. We see the exact P waveform similarity of 2 micro earthquakes in the Western Anatolia. The travel times difference at the common stations is about 150 milliseconds. These waveforms are shifted according to the time difference, and you can see the very good waveform similarity of these two earthquakes. If we assume the P wave velocity is about 5 kilometers per second around the focal area, the distance between these two events is less than 1 kilometer. We use two parameters to relocate the events. One is the coherence values at the different frequencies. If all values are larger than the 0.7, this is our threshold, we can say that these two wave shapes are very similar. If you look at the left-hand side of the figure, the waveform similarity is not good. The coherence values are very low, approximately most of them is 0. And we have no good cross-correlation function. On the other hand, at the right side, the coherence values is very close to 1 for all frequencies, and we have a good, very good cross-correlation functions, and we can see the waveform similarity at the bottom of the figure. The time shift is coming from the cross-correlation function time lag. This is about the 20 milliseconds for these events, and the waveforms are shifted 20 milliseconds, and we can see the waveform similarity again. This is an P waveform similarity at 3 common stations of 2 narrow earthquakes in the Suajik Bay. This is the Zeytineli stations, this is the Beyler stations, and this is the Doğan Bey stations. And the events are, the waveforms of the events are plotted with solid lines, and the other is plotted with the dashed lines. You can also see the waveform similarities again for the P waves. And these are the cross-correlation functions. And we have time shifts for all 3 stations. And we have good cross-correlation values for the frequencies between the 1 and 10 hertz. After relocating the earthquakes, we also determined the focal mechanism in this study. We used the P wave first motion polarities and the regional moment tensor solutions, and also teleseismic waveform inversion for much more larger events. Now, at this time, I try to show some seismicity properties of first Karaburun Peninsula and the Kuşadası Gulf, and finally Samos Island at the end of this presentation. If you look at the historical earthquakes in the region, the previous presenters, researchers are mentioned them. The historical earthquakes show that the region suffers from destructive earthquakes, and we look at the background seismicity and the focal mechanism solutions in the catalogs. Generally, normal faulting and strike slip faultings are occurred in the Karaburun Peninsula and around the Samos Island. And these earthquakes are large, generally larger than the 6 moment magnitude, and these are the destructive earthquakes for the region. And I think the similar events will occur in the future. In this presentation, but we focus to much more smaller events. First, the first cluster seismic activity in micro activity is observed in the Suajik Bay. The 2005 activity shows the 2 perpendicular faultings in the Suajik Bay and the southern part of the Karaburun Peninsula. The main shocks in this activity mostly shows the right lateral strike slip mechanisms, and their magnitudes are between the 5.4 and 5.9. And the larger aftershocks generally shows north-south, approximately north-south left lateral fault plane solutions. This is the first good observations, micro earthquake observations in the region, but because there were no dense seismological network in the area previously, the previous micro activity could not be known for the region. And then 2007, we installed several seismic stations in the area in the Turte project. You can see here with the triangles. And the earthquake clusters in the region become more visible. We also add the data from the Samos stations to better observation for Samos and Kuşadası activities. On this map, you see about more than 13,000 events in the area with the magnitudes larger than the 1.5 local magnitudes. And there are also approximately 7,000 smaller events are not shown on the map to better presentation. Now, first, I want to zoom to the Karaburun Peninsula, but I want to mention the 2 big events in the region. One is the 1992 Doğanbey earthquake, and the other is the Seferihisar earthquake in 2003. Their magnitude is the 6 and the 5.7 respectively. And the other earthquakes are much smaller than these earthquakes. But the important point in this area, we observed a dense seismic activity on the southern part of the Karaburun Peninsula. This is the Karaburun seismic zone. There is no clear mapped fault in this area. This seismic zone extends from the Suajik Basin and in the south and to the Gerence Bay in the north. And all focal mechanism solutions show clear southeast, northwest, left lateral strike slip motion. In this seismic activity, certain part of the Karaburun seismic zone show interesting cluster behavior. Here is the Uzunkuyu intrusive area, and there are several earthquake clusters around it. The first activity we observed occurred in cluster U1 here. The red circles show this activity, and the other 6 clusters in different places activated in different periods, and there are different number of earthquakes in each cluster. These periods are changed between a few days and a few months. This is not characteristic only here, but also for Kuşadası and Samos area. We can observe active clusters. Some clusters activated in a period and then become silent for a long time. If you look at the more closely around the Uzunkuyu intrusive, there are 4 district cluster here, and the Uzunkuyu intrusive is located in just between the 2 clusters, cluster 1 and 4. Around this intrusive, we can see the limestone units from the geological observations. If we look at the cross sections of these clusters at the left side of the figure, we can see a seismic gap between these 2 clusters. And this seismic, less seismic area in the upper crust may show us the deep extension of the intrusive in the upper crust. And here is the outcrop locations of this intrusive. And it's very coherent with these observations. And let's look at another area. This is the İzmir Bay. İzmir Bay is also active area. There are several normal faults in the bay determined by marine seismic studies. And the recent moderate, there is one moderate event in the bay. Occurred in 2012, close to Foça town, and this is important. These activities are important because these are very close to the city of İzmir and may generate larger earthquake in future and affect the region. Because of the activity of these normal faults. I think the Professor Derman Dondurer in the next talk, we will give more information about these normal faults in İzmir Bay. And if you look at the other area, Samos Island and Kuşadası Gulf area, in the Samos Island and Kuşadası, we also determined several clusters with high number of events. And the largest event in this period is about 4.9 occurred in the south of the Samos Island. But the important point is that these micro earthquake activities to show us the faulting properties in the region. onshore and offshore earthquakes around Kuşadası shows a clear normal faulting mechanisms here. And their depths of the events are generally between the 5 and 15 kilometers. Because there are several close faults in the area, it is difficult to identify them using the micro-earthquake activity. Our improved locations is not precise to identify each fault on the land and maybe in the marine area. In the previous sessions, poster sessions, some studies are presented for this area. Savaş Güçay show us some normal faults in the Kuşadası Bay to southern dipping and the northern dipping, and are very close to each other. But we can observe the size of focals in a narrow band from surface to the deep part of the crust, but it's difficult to say that these are this normal fault or this normal fault, as mentioned before. There are also some small clusters around the Samos island, and there is not enough large earthquakes to determine the focal mechanisms. Therefore, we try to solve the joint solutions for the P wave first motions. And here examples, 3 examples. And one is occurred on the Samos Island, close to Karlovas area, number 21 event. And there are 9 events in a very close, in a 1.5 kilometer radius, occurred in a small volume, determined from the double difference inversion. And if you look at their first motions, they are good. They are in good agreement to determine mechanisms, and all of them show a good normal faulting in the area. If you look at the cross sections of the different clusters in the region, we clearly visualize the Samos faults in depth. For example, south dipping of the Pythagorean fault, it extends to the depth of the 10 kilometer. In the north of the Samos, we also identified 2 district clusters, and these are the important because they are very close to the latest Samos destructive earthquakes.
Last 2 minutes, Onur.
For?
Last 2 minutes.
Okay.
Delta, please, yeah.
Okay. And these are the latest slides. Okay. And the latest earthquakes just occurred the 2 destructive clusters north of the Samos. And there are also, as you know, there are also a lot of aftershocks in the region. And for example, this aftershock area is the reactivated of the previous cluster determined in the previous our studies. Okay, we relocate the first 42-day aftershocks and using the double difference algorithm, and their location, focal locations are the very has very low uncertainties, and we also obtain the rupture propagations of the main shock. Both teleseismic and near field strong motion waveforms were inverted simultaneously. The observed and calculated waveform shapes and their amplitudes are in good agreement, as you see in the waveform shapes. The inversion results indicates 900 kilometers square total rupture area for this event, and there are 3 high slip patches here, A, B, and C. The largest slip is 1.1 meters in the patch of A, and another second patch, high slip area, located in the west of the focal of the main shock. And the previous 2 clusters here plotted with blue circles are just around the maximum slip area, as you see. And the aftershocks are observed on the generally on the unruptured slip areas because of the stress relaxations after the main shock. And we also determined the rupture propagations, and these are the selected time frames of the rupture propagations. In the first 5 seconds, the rupture propagates circular, and then to move to the west and stop it about 25 kilometers away from the focal point of the main shock. And the aftershocks very away from the main shocks may be triggered because of this rupture propagation. We also calculate the Coulomb stress changes, and all aftershocks are located in the positive stress change areas. It's clear most of the aftershocks, about the 75% of them located in the positive Coulomb stress area. And finally, I want to show the latest 3 events occurred in Gümüldür town. And these are in the same place with the 1999 Doğanbey earthquake. It's the largest event in this area. These 3 events are in the negative Coulomb stress change law of the Samos main shock. Sorry. Oops. And we may say that these are not triggered by the latest destructive event, but as Professor Pavlidis said in the poster sessions, who knows, because the area is a very complex stress regime. And okay. Here is the conclusions. I put some main points, and earthquake activity observations with dense seismology networks in the Western Turkey clearly shows the earthquake clusters. The events clusters are active in a period 2 or 3 days to a few months, then become silent. The Samos earthquake occurs between the 2 micro-earthquake clusters observed in 2007 and 2012. The cluster may indicate the possible location of future large earthquakes according to our results. And it's evident that the micro-earthquake observations down to the magnitude 1 with dense permanent seismic stations must be performed in Turkey, also in Greece. And the final common earth size studies should be increased between the Turkey and Greece. And you can find our results in details in these 3 papers. Thank you very much.
Okay, thank you, Dr. Tan, for your interesting speech. And we can now directly move on to the next presentation, as we have no question for your talk. So the next question will be given by Professor Derman Dondurur and his friends on the active faults of the Izmir Gulf using high-resolution seismic data. If you are ready, the floor is yours, Professor Dondurur.
Orhan Hocam, I'm ready. I'm trying to share my screen.
Okay.
Do you see the presentation now?
That's fine. Full screen, please.
Yes. Now, is it okay?
That's perfect. Yes. Yeah, you can start
Okay.
now. Okay. Thank you.
Thank you, Orhan Hocam. Good evening, everyone. In my presentation, I'm going to show you several high-resolution seismic sections from the Izmir Gulf, which illustrate the existence of the active fault systems and their extensions in the area. By means of structural setting, the Izmir Gulf and surrounding region is quite complex, with both interacting normal and strike-slip faults. It's actually a local area within the complex structural context of the Aegean region. The onshore extensions of the faults are known actually very well, but their offshore extensions have generally been predicted. So the seismic data here will illustrate the current active fault systems and their extensions within the Gulf. The Izmir Gulf is a shallow basin that is still being developing. The whole Gulf can be divided into three main parts. The inner Gulf, where the Izmir city center is located around. The outer Gulf, which opens into the Aegean Sea in the north, and the Gulbahçe Gulf at the southwest. The maximum water depth in the inner Gulf is 20 meters, while it's approximately 65 meters in the outer Gulf. Of these, only for the outer Gulf, the extension of the active faults were mapped and tectonic models were developed. So I will mostly speak on the outer Gulf in this presentation and show you some basic seismic data examples from that area. Gulf of Izmir and the surrounding regions have been deformed by the northwest, southeast, and east-west trending fault systems. The most evident active faults are seen in the small map in the middle. They are the Izmir Fault, Gulbahçe and Tuzla Faults, and Karşıyaka Fault zones in the onshore part. Different fault models have been suggested by different researchers for the area. This slide shows the main results of some of these studies. Ocakoğlu and others suggest north to south trending strike-slip faults for the Gulf. According to Aksu and Uzal's study, the outer Gulf is characterized by northwest to southwest extending normal faults. These interpretations are based on the marine seismic data collected by Aksu and others, and provide an impression of the faults within the outer Gulf. In order to characterize the active faults in the whole offshore area, we use 3.5 kilohertz sharp, 5 kilohertz sub-bottom profiler, and 400 hertz Sparker single-channel seismic data collected in the whole Gulf. Here you see the coverage of the seismic profiles. The penetration of the chirp and sub-bottom profiler system is about 30 meters, while it's about 100 meters for the Sparker lines. We also use the multi-beam bathymetry map multi-beam bathymetry data to map the morphology and possible lineaments due to the surface expressions of the active faults. Okay, this map shows the effect of the ancient Gediz River on the outer Gulf and fluid flow structures in the area. The ancient Gediz River bed in the central part of the Oder Gulf was active until the end of 1800s. Then the riverbed was moved to the outside of the Gulf. Anyway, it has a considerable effect on the formation of the present-day morphology of the Outer Gulf, since it has controlled the sediment accumulation in the area. Through the northern border of the Gulf, acoustic turbidity zones, gas chimneys, and active or inactive pockmarks commonly along the fault planes exist in the seismic lines and are interpreted as biogenic gas accumulations produced in organic rich high-stand sediments from the Gediz River. Okay, let's start with the Outer Gulf. To the northernmost part of the Gulf, just east of Uzunada, seismic data indicate the existence of a narrow young graben named Izmir Central Graben. The formation of this graben seems to be ongoing since it creates deformation at the seafloor. Aksu and others mapped the continuation of this graben at the end of the Gulf to the all the way north. Towards the south, the graben gets narrower and disappears at the east of Uzunada. In this region, a new identified active fault from Foça to Suzbeyli village also exists and named here as Foça-Suzbeyli fault. The western part of this fault is the hanging wall block. Similar to the central graben, it's a very young fault that crosses the recent sediments. In addition, the apparent thickness of the sediments changed at both sides of the fault, which indicates a sign sedimentary fault pattern. It's impossible to follow this fault on land because of the swamp conditions on the surface in this area. The most prominent fault within the Outer Gulf is Uzunada fault zone. Is observed as a single fault scarp at the southernmost part of the Güzelbahçe down here. In this region, it has a vertical slip of about 5 meters here. Then it extends towards the northwest until the Çiçek Islands here, where it splits into many segments. These segments composed of 3 fault scarps extending to the northeast of Hekim Island, and they show a left lateral slip in this location. The segmentation of fault here at the north of Uzunada around this location is important since it may indicate the clues of the fan-shaped opening of the Gulf. Uzunada fault extends to the land ground around Güzelbahçe, and yet there is no detailed mapping of this fault on land. This slide shows 3 Sparker seismic lines cross-cutting the Uzunada fault in the Outer Gulf. It deforms the seafloor and this shallow subsurface sediments all the way down, as you see. According to the seismic data, the normal component becomes dominant towards the north around Uzunada, where the throw rate of the fault increases towards the deeper parts. However, to the south, it exhibits strike slip characteristics such as transpiration clues, which indicates the bending of the fault. In addition, irrelevant reflective surfaces exist at both sides of the fault around the Çiçek Islands here. For instance, the regional base of the deltaic sediments in here and here cannot be peaked at the left side of the fault, These observations may indicate a significant strike slip component for this fault in this region. In the southern offshore, the Izmir fault is the only fault traced in this study parallel to the shoreline, extending in this direction. Izmir fault was considered as a wide fault zone in the onshore part of the Gulf. According to the seismic data, Izmir fault is extending in the offshore as a single normal fault at the western part of Balçova. Offshore length of this fault is about 10 kilometers, and it cannot be followed after Güzelbahçe towards the west. It finishes here somewhere. Okay, this is the main fault map of the Outer Gulf, showing the extensions of the faults deduced from the seismic data. It shows the Uzunada fault zone, Izmir fault here, Izmir Central Graben, as well as Foça-Suzbeyli fault to the northeast. Both Uzunada and Izmir faults are quite distinct in the multi-beam bathymetry map of the Outer Gulf as a prominent lineaments. Both faults are the most critical active faults close to the urban area of the Izmir city, yet they are not evident in the onshore region, except limited onshore extension of Izmir fault zone to this south here. The Uzunada fault zone indicates the complex opening mechanism of the Gulf. Along the Izmir Central Graben and Foça-Suzbeyli fault, it seems to control the extension of the Outer Gulf. The strike of Izmir fault is completely in east and west direction, in contrast to all recognized other faults. Okay, when we come to the Gülbahçe Gulf, the things are getting quite complicated. This slide shows 3 chart seismic profiles from Gülbahçe Gulf. The faults here show quite complicated, and they contain significant strike slip faults, faults with dominant normal components, and possible transpiration clues within the sediments, which are all observed within a relatively small zone of interest. The faults of the Gülbahçe Gulf on land section is actually very well known. However, the faults within the offshore is generally indicated as a single fault, especially towards the northern part. But the fault structure of the Gülbahçe Gulf, especially at its northernmost part, is quite complicated and needs further investigation. Here we only map the fault traces using their surface expressions on the multi-beam bathymetric map. The distance between the parallel seismic lines here in Gülbahçe Gulf is only 200 meters, but structure also changed from one seismic line to another, making the mapping of the faults almost impossible, especially for the northern part. To the south, however, the structure becomes more simple, as you see in the seismic line at the bottom. Inner Gulf is investigated with single channel sparker lines. The seismic data from the southern margin of the Gulf, Inner Gulf, indicate normal faults with hanging wall block towards the basinal area to the north. The troughs of these faults are relatively small, and they show the clues of a geometry like a half graben structure. Here we see shallow gas accumulations at the northern part of the Inner Gulf, and we cannot map the faults in this region. However, there exist several faults typically affecting the erosional base reflection of the thick Holocene sediments in the central basin. In this part of the Gulf, fault seems not to create deformation at the seafloor, and there is no lineaments on the multi-beam bathymetric data attributable to a fault trace. However, the inner Gulf needs further investigation by means of a denser seismic grid to map the faults in detail. In order to summarize, we can conclude that the western margin and the southern part of the Gulf formed under the influence of Uzunada and Izmir faults. In the southern offshore, there is only one east-west directional normal fault, dipping through the north and corresponding to the offshore segment of the Izmir fault zone. We see from the local seismicity map that the majority of the earthquake magnitudes in the Izmir Gulf are generally less than 4, and the zone along the northern Uzunada fault, Foça-Suzbeyli fault, and the Izmir central Graben show a significant earthquake activity. Dr. Onur Tan actually mentioned the seismicity of the area in detail in his previous talk. The acoustic data show that Uzunada fault zone is a simple lineament near Güzelbahçe to the south. It then bifurcates towards the Çiçek Islands and terminates with left lateral slip in the east of Hekim Islands here. Then the fault extends in the northwest direction until the mid of Uzunada as a single fault segment again. Then the fault is observed as a bunch of many active fault segments like horsetail place to the east of Uzunada. Izmir fault also controls the northern extension of Seferihisar and Tuzla fault zones to the south, because they all terminate at the intersection points on Izmir fault and cannot be traced further north from the Izmir fault zone. In accordance with the extensional tectonic regime of the Western Anatolia, main faults could be considered as normal faults with strike slip components because of this transtensional characteristics. The end of each fault segment is characterized by the horsetail splays in the Gulf. In addition, extension of these faults was controlled by the northeast southwest directional tier faults to compensate the rotational movements within the Gulf. Okay, this is a hypothetical model for the area. The fault segments here though were chronologically succeeded from the east to the west. So this pattern indicates a westward extension of the Izmir Gulf with an anti-clockwise rotation, while the Karaburun Peninsula is rotating the clockwise direction. This pattern explains why the Gülbahçe fault zone is a right lateral strike slip fault. Similarly, the region to the south of Izmir rotates in the clockwise system, in contrast to anti-clockwise direction of the Izmir Gulf. This is the reason of dextral strike slip characteristic of Orhanlı or Tuzla fault zones. According to the relative GPS velocity field, fan shape extension within the Gulf is more rapid than the surrounding area. This also explains the horsetail place of Uzunada fault zone and why the Izmir central Graben starts from the eastern offshore of Uzunada. From the eastern part of the Hekim Island. Extension of Uzunada fault zone and Izmir central Graben are almost parallel to each other, and they are almost normal to the local GPS vectors. And this is another indicator of ongoing westwards opening of the Gulf. Additionally, a new fault extending from the offshore of Foça to Suzbeyli village to the south was identified. It shows the clues of a sedimentary normal fault related to the opening of the Gulf. The onshore faults are mainly the northeast, southwest direction. However, Uzunada fault zone, İzmir Central Graben, and Foça Suzbeyli fault extend angular to these trends in the outer Gulf. This may also indicate the active V-shaped opening of the İzmir Gulf through the north and northwest. These are the main conclusions of this study. The outer Gulf has active faults, mainly extending in northwest to southeast direction, named Uzunada Fault, İzmir Central Graben, Foça Suzbeyli Fault, and İzmir Fault. Especially Uzunada and İzmir faults are significant in the bathymetric map based on the active faults of the Gulf. Outer Gulf seems to be opening westwards and rotates counterclockwise direction. Outer part of the Gulbahçe Gulf is quite complex by means of structural setting. It contains strike-slip faulting interrelated with transpirational structures and needs further investigation to obtain the tectonic setting and its connection to the with the faults on land and in the outer Gulf. The faults of the inner Gulf are all buried beneath the Holocene. We obviously need more data to define the faults of the inner Gulf and their interconnections with the surrounding faults observed on land. The deep seismic data from the İzmir Gulf is quite limited to define the deeper setting and stratigraphy. The only deep seismic data is collected by MTA in 1996, I guess, and interpreted by Ocakoğlu and others. It's suggested that the deep multi-channel seismic data along the outer Gulf can provide valuable information about the structure of the Gulf. The active faults of the Gulf should be taken into consideration in the preparation of the earthquake master plan of the city, with a possible connection with the local seismicity. I think that's all. I thank you for your listening and participation.
Okay, thank you very much, Professor Dondurer, for the presentation and also completing just on time. And we have, I think, no questions on the Q&A section. Well, I think one question, yes. Can you read that from your screen? There is a question from Onur Tigli, so I will read it for the other attendees. As I understand, you consider that you might be Uzunada fault, slide figure C, transpiration zone due to structural component of fault. Is there any supported strong clue of this hypothesis apart from bending of layers as similar to bending on a reverse fault? Professor Dondurer.
Okay, actually, this is a nice question. We see this transpiration clues on these Parker seismic lines, relatively deeper seismic data than the chord or sub-bottom profiler, but unfortunately, we have very limited extension of these Parker seismic lines in this area. So we have only 1 or 2 seismic lines indicating this bending or folding of the sediments. So it's not easy to get conclusions from these limited seismic data coverage that the fault is bending towards some other direction, or are they all transpirational structures or something else? It's not easy, but that was our interpretation. Actually, the seismological data may support this hypothesis. I don't know if there is any focal mechanism solutions for the earthquakes in the outer İzmir Gulf, especially offshore of Güzelbahçe, where we see the transpiration. If Onur Tan or other seismologists can contribute on this, we can discuss.
Okay, so any more contribution, Onur or other friends?
I think that there is no much more fault mechanism solutions in the Gulf of Izmir, and because the events are very small, and as I previously said, that there is no good seismological network in the region. Therefore, we cannot able to get focal mechanism solutions in the area.
Okay, so thank you very much, Professor Dondurur. Thanks for the question, Mr. Onur Tığlı, and for your comments, Dr. Tan. So we can now move to the next presentation that will be given by Nasim Muzaffari and her friends, mostly from the University of 9 Eylül and also from Afyon University. So the title is Beyond the Historical Records in Western Anatolia, Cosmogenic 36 Chlores Direct Tracker of Normal Fault Activity. I think she will join us from Switzerland. Are you ready?
Yes, I'm trying to
Okay, so
share my screen. Thank you. Just a minute. I hope everyone can see my screen.
Yeah, full screen, please.
Yeah, okay.
Thanks.
Good afternoon, everyone. However, I'm not connected from Switzerland. Now I'm in Canada, so it's morning already. Yeah, first of all, thanks all the committee member for organizing this virtual workshop and inviting me. I'm talking about application of fault scarp dating using colorine 36 to track activity of normal fault in Western Anatolia beyond the existing earthquake records. For sure, everyone here is familiar with this figure, so I'm not going into the detail. Everyone knows that how Turkey is active and aware about the Samos disaster. So I just go to the main issue, like everywhere in the world, that the main issue is always the lack of data and the time span that all these historical and instrumental earthquakes are recorded are not really long enough to enable us to assess how often destructive earthquake happens and to determine the amount of displacement and also to approximate the timing of future ones. So with this knowledge that the area is already active, we did fault scarp dating in Western Anatolia with the aims of determining the age of past earthquakes, the amount of vertical displacement, the magnitude that was responsible for these ruptures, recurrence interval, and approximate timing of future ones. So this is simplified geological map of Western Anatolia, which is geomorphologically characterized by east-west trending grabens, which consist large-scale normal faults, which are locally built in limestone. And this makes this area an ideal place to apply fault scarp dating using colorine 36. What we did is we selected seven key normal faults in 3 in Gediz Graben. We have Rahmiye here, Mugir Tepe, and Monastir. And along the Büyükmenderes Graben in its western part, we have Kalafat, Yavansu, and Priene-Sazli. And along the Gukova Graben, we sampled Oren fault. We did sampling for fault scarp dating of these faults. I just proceed to our method. Actually, our method is based on reaction of cosmic rays with the normal fault surface. Just imagine in this figure that we have a fault here. It's exposed here, what's covered by collovium in the lower section. we show concentration of chlorine on this axis along against the position on the fault scarp here. So you'd see that for the exposed part of the fault, we have a constant amount of chlorine-36 production, but below the surface, because of the shielding effect of collovium, the production is decreased towards the depths. In this animation, I just show you how the chlorine-36 concentration pattern looks like when we have 4 similar earthquakes of similar size. Again, imagine we have a fault here. It didn't rupture yet. It's totally covered by collovium. So at T1, we have the first rupture and with the slip amount of S1, and the ground level moves from G0 to G1. So for the concentration of chlorine, we have such a convex form. Just compare with this figure. So this convex form shows the time that the fault surface was already covered by collovium. And the time passes, we have the second rupture at T2. Again, we have a slip of 2 and the time of inactivity, but this sharp discontinuity between these two convex forms represent the timing of earthquake. And then we have at 3T and 3-4, finally the last earthquakes, and the ground level, I mean the collovium level finally reached to the current ground level that is here. So if we build up all this concentration, we have such a pattern for the chlorine-36 concentration, and this is what we model in fault scarp dating using chlorine-36. What we did in the field. Actually, I'm not going into the detail for all of these field, I mean the faults, but I just show you all the figures from the field work, but mostly focus on the results from Calafat and Yavansu. For sure, they are not directly related to Samos earthquake, I mean the fault responsible for the Samos earthquake, but they are kind of aligned with that. So I decided just mostly focus on this faults. So first we go to Gedizgraben to show you Rahmiye, Mugirtepe, and Monastir faults. This is our this is the Rahmiye fault from the I mean far distance. This is our sampling site, and in a closer view we have this. It's a really flat and nice fault surface. So we have some Roman excavation here, and we just did sampling right here. That is looks like this. First, what we do is we mark all the samples on the fault scarp like this. It has dimension of 10 and 15 centimeters, and then the profile should be continuous from the ground level upwards the fault surface. So we collected 87 samples here. And also what is important to be measured is geometry of the fault. I mean, the scarp deep, top surface deep, collovium deep, scarp height, and also another important thing is to determine the exact top and bottom position of each sample. This is Monastir fault scarp. We had three profiles, sometimes because of this kind of patches and high amount of erosion, shifting for a few meters is allowed for this method. And then the geometry of the fault is shown here. And the Mugirtepe fault just close to Monastir. And then we move to western part of Büyükmenderesgraben. We have Calafat fault and Yavansu here, and Priene-Sazli here. I mean, sampling site is here. Actually, Calafat and Yavansu fault are considered as the displays of long Kushadase fault zone, which are kind of aligned to the fault that is responsible for Samos earthquake. So these two are located on the opposite side of a hill, Calafat mountain. We go to the field. This is the trace of Calafat mountain here, and the closer view. you see that the fault surface is almost vertical. So normally to have access to the upper side of the fault, we use a scaffold. And you see the 54 samples is collected here, and geometry of the fault is shown. Move to the other side of the hill and go for sampling for Yavansu. 68 samples are collected here. And you see, again, because of these patches, we just shift a little bit to the left for the upper side of the fault. And another important thing is that determining the reference point. Reference point is defined as the collovium level just after the final earthquake model. So we just define this by looking at the surface and difference of freshness between the exposed part of the fault and already covered part of the fault by collovium. So here, the reference point is determined to be here. So we had like 4 to 5 samples just below the ground. More to the south, pre-Renaissance fault. This is the fault trace. Sampling site here. 4 profile are installed here for collecting samples. And a closer view, 117 samples are collected, and geometry of the fault is here. And along the Gokova Graben, the Oren fault has been sampled. This is our longest and highest surface, the fault and surface collected. It's already 12 meters long. You can see from here how high the fault surface is, and about 130 samples are collected here, and it already has a record of a recent disaster at 2017 and geometry of the fault. And our lab work, I don't go through all the lab procedure here, but I just briefly say that we almost treated like about 600 samples for AMS and the other elemental analysis. And these are our results from Calafat and Yavansu without any simulation. Again, we have concentration of colorine here against position along the fault scarp. So each of these points represent concentration of colorine in individual samples along with their uncertainty. And you see that we have like 4 samples below the ground collected. And how we model. We use a MATLAB code using written by my colleague, Dmitry Tikhomirov. Name is fault scarp dating tool. First, we build our database based on all the input parameters like geometry of the faults and all the AMS and other elemental analysis. And then we run the code for modeling based on different scenarios in terms of the number of earthquake, the age of earthquake, and also the amount of displacement that occurred during these ruptures. And finally, the most realistic result will be selected based on the less difference between the measured and theoretical ones. So for the Calafat fault, we could model 3 earthquakes, about 15.3, 8.4, and 3.6 thousand years ago, with the slip amount of about 1 to 3 meters. So this is the oldest one, and then the youngest one we have here. And the slip rate has been calculated. And for the Yavansu fault also, we have 3 earthquakes recovered, about 8 kilo years ago, 3.4 and 2. And with this amount of displacement, and slip rates are here. Here I just summarize the time slip history of these 2 faults. We have Calafat Mountain. Calafat fault is in the north, and Yavansu we have here. The earthquake model for Yavansu are here, and Calafat are shown here. So we see that the Calafat fault first had a rupture, and then when it had the second rupture, almost at the same time, Yavansu got ruptured too. And the youngest ones are also more fitted. You see the age is 3.4 and 3.6. And finally, we had a rupture in Yavansu fault. So to control the plausibility of modeling, we used empirical relationship, and regardless of modeling actually first, and then to see how big earthquake we can expect if these faults are activated and how much displacement that they can produce, and then compare with our modeled displacement, and found out that these earthquakes, especially these younger ones with a larger amount of displacement, they are consist of like clustered earthquake. The earthquake that just occurred close in time, that unfortunately the code is not able to detect them as individual earthquake. I'm not going to show you, because lack of the time, not show you all the results from the other faults, but I just compiled all the output here. You see the ages for the earthquake are here, and they are nicely correlated somehow. And for example, Pre-Nasazli and Oren fault show recurrence interval. Their recurrence interval are regular and show like 2000 years of difference. And then slip rates are in general increasing through the time. And the earthquake responsible for this rupture were mainly in average 6.5. In this graph, I just plotted all the ages along with the uncertainty. So at least 20 major seismic activity over the last 16 years has been recovered, which most of them occurred as clustered earthquakes of magnitude in average 6.5. If we consider the age correlation, we can somehow say that every 2000 years, we can introduce like 4 activity phases, and which almost simultaneously all of these faults were activated. And in addition to our time with the frequent record of frequent earthquake, we can say every 1000 years we have a really high seismic activity. And some of them are perfectly correlated with the historical records we have here in Monastir, and the other one on Pre-Nasazli. The historical records are these ones. Now I just zoom out a bit more from the Western Anatolia to a regional scale of Aegean Sea, and to take a look at the other normal faults in this region, in Italy, Greece, Turkey, and Israel. And what was interesting was that in general, this recurrence interval is kind of common between the normal faults of almost similar size in this region. Now we can connect the deformation pattern of Western Anatolia with the faults that we studied. Actually, everyone knows that African plate is being subducted beneath the Aegean plate, and because of this, on the African plate, we have a formation of strike slip and lots of thrust faults as a result of shortening. But in Aegean, above the Aegean plate, and especially Western Anatolia, due to back arc extension procedure, lots of normal faults are formed. So, and the exact amount of this, this convergence is not clear yet, but the number between 10 to 40 millimeter per year has been estimated. So these large movements just transmit a large amount of stress on the faults in Aegean plate, and especially Western Anatolia, and especially on the faults which are parallel and subparallel to the convergence trend. And more stress will be loaded on the larger faults. And part of this energy is consumed as seismically consumed. So that's why we have a frequent and a large amount of earthquake on this side. So and anyway, we cannot stop this earthquake from happening, but with every polar earthquake study we do, we can just take a step forward for better seismic risk assessment and also to help to minimize the value of damages. And the slip rate that we calculated is up to 2.4 millimeter per year for the faults, which in general increasing through the time. So it can kind of indicate that the faults in Western Anatolia are not mature. I mean, they are still propagating and they're tightly interacting with one another, and their stress field is tightly influenced on each other. And also, it can tell us that our time with records of very large earthquakes and frequent earthquakes can be considered as the most active period during the Holocene time. To sum up, we recovered at least 20 major seismic activity, mostly as clustered earthquakes. We introduced 4 phases of high seismic activity with at about 2, 4, 6, and 8,000 years ago, and with the recurrence interval of almost 2,000 years, which fits somehow to a series of normal faults in Aegean plate. And most of the faults are seismogenic, and actually all of them. And the slip rate acceleration shows that our time is the most active period through the entire Holocene, and the fault of Western Anatolia are still propagating and growing. And what about the next high seismically active period? With this finding, it's not far beyond expectation that we have the next one in 2,000 years. Thank you so much for attending, and if there is any question.
Okay, thank you very much, Dr. Mozaffari. So we can have maybe 1 or 2 questions from the audience, as we have no question on the Q&A section of the Zoom application or YouTube channel. If any.
Ran?
Yes, Ricardo, please.
No, I was wondering, very nice work, a lot of data. I was wondering how archaeologists left you cutting and destroying the archaeological site, nearby the archaeological site.
Oh, it was
would be impossible in other.
Yeah, it was impossible inside it, but we just moved a little bit. I think it was like 5 kilometers away from the Soke site. Just behind the olive trees, so we were somehow hidden.
Okay. Good job.
Thank you.
Okay, thank you very much.
And actually, sorry, another thing I should add for this site, Rahmiye fault, that it's already kind of excavation by Roman. There were two government person, I don't know from which, they were watching us all the time, because it was supposed that there is a treasure already. And if you noticed, when I showed the false scarp surface, there was a dynamite explosion there. It was already, yeah, because it's supposed to be a tomb, I mean, but nobody knows. But we could find our treasure, actually.
Okay, good luck.
Thank you.
Okay, thank you very much, Nassim, for joining us from Canada.
Thank you.
And have a good day and stay healthy, please. Yeah.
Thank you. You too.
Bye-bye.
Thanks. Bye.
Okay, so we have now come to the final presentation of the workshop, which will be presented by Spiros, who also presented the first talk of the workshop. So he will also close the workshop. So the title of the presentation is the Northern Thessaly Strong Earthquakes of March 3rd and 4th and their neotectonic setting, preliminary results. Yes, the floor is yours, Spiros.
Thank you. Can you see my first slide?
Yes, and the full screen, please.
Okay. It doesn't work to the full screen. I don't know why. Oh.
There, yes. There you're fine, yeah.
Is it a full screen?
Not yet. I guess there is a problem with your application. Just enlarge it a bit, maybe.
I will recall it.
Okay.
No, just I will enlarge. No, it did not respond.
Anyway, so we can follow your
Can you see? Can you see this?
Yes, it is. Yeah, sure. We can see it.
If you can, neither. Oh, and now enlarge.
That's fine. That's fine.
Okay, now it's a full screen.
Oh, that's great. That's
okay.
Great.
Good afternoon. Let's relax a little and move from the Samos earthquake and surrounding area because exactly after the Samos earthquake, 4 months after this earthquake, another strong earthquake occurred in central mainland Greece. So I will try to give in brief some preliminary results of this earthquake. You can see of different focal mechanisms from different institutions, and you can see northwest, southeast trending faults. First of all, I would like to mention that the area of Larissa Plain, Thessaly Plain, which cuts a mountain range, the highest mountain, the Olympus, first mentioned by the historian Herodotus from Halikarnassos, today Bodrum, and you have there a statue in Bodrum of Herodotus. And he says that it seems to him that this narrow valley, the Tembi, is the creation of earthquakes in the separation of Olympus from the other mountain, and gave an exit to the Thessaly Plain lake, the waters. So a sequence of earthquake occurred on March 3 and 4th in northern Thessaly. The first one was magnitude 6.3, and it followed by a 6 point or 6.1, and 2 aftershocks of 5.6 and 5.2. Here you can see the historical earthquakes and instrumental seismicity of the area, the focal mechanisms of all these earthquakes, the same trend of the fault, while the area is well studied, and the most of the active fault characterized as east-west trending, or 110 degrees from the north. And this was the study area from PhD of Riccardo Caputo from 1989. In previous historical research have been referred two strong earthquakes, among others in Thessaly, that of 1735 1905 and 1901, which we believe that they associated with the same area of the last earthquake. A strong earthquake occurred 8 years ago in the area, 1941, the same magnitude in the city, the capital of Thessaly, Larissa. Here you can see the aftershock distribution. The first day, and the 24 hours, after 7 days, and after 1 month. They are concentrated and they are more or less linear along the very well-known faults of Tyrnavos and the extension of the Larissa fault to the Titarisios River, to this river, also well-known fault. Damages to buildings and collapses concentrated mainly along the Titarisios Valley, where is the distribution of aftershocks, as you can see, and in this part of the Pinios River close to capital Larissa. Interesting is the alpine geology, because the area is of Pelagonian zone, geological zone, here, and it consists of schist, gneiss, and marbles, and it is a very complicated, they are pre-Paleozoic, Paleozoic, which deformed during the alpine deformation as well, and there exist, as you can see, there is the mountain Olympus, which is a window, a geological window, a tectonic window. There exist large normal faults, low angle, and the revelation of underlying zones from tectonic windows. The extensional tectonics has played an important role from the tertiary unique to today, with the extensive shear zones and detachment faults. According to Kilias and his colleagues, the area was compressed, of course, during the alpine compression, and then during the end of Oligocene, early Miocene, and late Miocene to Pliocene, it was extension. So, as you can see from Greek databases of seismogenic sources, a very well fault, it was the Tyrnavos fault, where Riccardo Caputo spent more than 30 years to study it, a typical active fault, and now the area studied mainly by Riccardo Caputo and others during master and PhD thesis, and it's continuing. The neotectonic regime in seismogenic sources, you can see that the statue of active stress is that we have two directions, an older one, northeast south west extension in the broader Aegean, and the active one as north to south. Here you can see by my Professor Mondrakis in more detail in the area. While it separated the older with yellow, with the active with the normal by Mercier first, and many others up to recently up to focal mechanism. In this map is the detail of the seismogenic sources in the Gredas and the year of provided measure earthquakes. Another important is that think in this part of the seismogenic area of the last earthquake suggested by the Geological Survey of Greece, that, as you can see, the synthetic stratigraphic column of neogen formation, because of the interest of lignites, And the profiles that you can see on borehole data, where is the alpide basement, the base formation of the Miocene, the lignites, and early quaternary and Holocene deposits. There are faults of north-south and northeast that we believe to be of inactive, older faults determined by boreholes, but ground deformation phenomena occurred during the last earthquakes. And as you can see, again, the extension of the Tirnavos fault and other known active faults in the area along these faults like cracks and liquefaction, linear liquefaction phenomena. My colleague Alexandros Hatzipetros earlier afternoon show you the geodesy, two examples, GPS geodesy, which here in this picture, you can see representative maximum horizontal extension in red and compression in green. The maximum horizontal extension parameter shows a dominant north-south direction, which is consistent with a known stress field of the area of Aegean as well, and the active faults, but however, a distribution of some east-west trending maximum horizontal extension vector is also documented. The data existing only few GPS permanent stations. You can see here the horizontal co-seismic displacement in the broader area, and one of the permanent stations in the nearest to the epicenter city town of Elassona, the permanent session, and the displacement is north during the earthquake. Let's see some environmental results. First, extensive liquefaction phenomena from different places. Here you can see a linear or sand craters, sand volcanoes. Again, linear here. And here is in the detail composite, the yellow border here you can see in this place, overprinted to satellite image clearly shows that the distribution of individual liquefaction features, that you can see some gray here, curvatures, coincide with an abandon of field bends of Pinos River. The current river bend is visible here, while there, and some of the linear liquefaction phenomena follow this. Also, rock faults, cracks and landslides occurred, mainly across the Titarisios River. Here's Larissa, Pinos River, Titarisios River. Interferometry. Immediately after the earthquake, you can see here the epicenter. Our colleague Fumelis from our laboratory appeared these INSAR pictures, and as well as by Ganas, Valkaniotis, and Tironi. And a few days ago appeared another interferogram, and more or less are the same, as you can see how linear. We followed this of our university. And let's say which was the seismogenic fault. First, we believe that one of two very well-known faults active faults, well-studied active faults. And as you can see from the model of acceleration, somewhere there a fault was activated. But the focal mechanism, as well as the aftershock distribution, as well as the interferometry, they show a different place, where not in the soft sediments, not in those folds with a clear and typical morphotectonic surface expression, but on the Paleozoic basement rocks of Pelagonian. Let's see, and we are concentrated there to look for evidence of the possible fault traces. And as you can see, as far as the infos are unknown and unmapped seismic fault concerned, Feldward showed that there are characteristic geological indicators in the Pelagonian zone consisting of Paleozoic mica schist and gneisses, mainly indicating that a low angle normal fault has acted as a hidden or blind fault. Here you can see some cracks on the gneisses, it's the soil, and some other features, and fault surfaces of 50 degrees dipping, like this one. Also, the seismic fault modeled as a seismogenic source, and here is a preliminary results. The seismic fault of the main soca here, the Columb static stress changes, taking into account that the depth of the earthquake was 8 kilometers, and here you can see a vertical cross-section normal to the source strike. This is here. Results show stress load beyond the tips of the fault, suggesting a triggering scenario for faults of similar geometry and kinematic in reds. The main coseismic fault cannot be related so to the hitherto known faults in the area. The Feldward has shown, as you can see in this map and the reference here. Analysis of data of the interferometry, and they show that the main seismogenic structure is neither the Tirnavos fault or Ralesa fault. But as we know, the area from tectonic point of view is very complex. Complex tectonic and synorogenic collapse, but also exist normal low angle detachment surfaces that believed to be inactive. So once again, that the dominant opinion was that north east-southwest is the old direction, and this north-southwest the active stress, the extensional, the sigma to the 3. As concluding remarks, we can say that a low angle normal fault was activated for the main as a blind or barrier fault following pre-existing inherited alpine structures that does not appear to have a superficial appearance. They have no typical morphotectonic criteria like other faults. The strongest aftershock or second main earthquake of 4th of March, 6.1, is located from the same rupture site, but may have occurred from a minor segment of the same fault in the seismic sequence a little bit northwest. The active stress pattern of the upper crust of the area has been characterized by an extensional direction to north-northeast, south-southwest. This is based on both quaternary neotectonic quantitative methods and focal mechanisms of recent earthquakes. The older Neogen-Pliocene extensional field had a different extensional direction. The Neogen quaternary Elasson-Potamia basins show that in addition to the east-southeast west-normal-west direction of faults that we believe to be the only active faults which are appropriately oriented in the active tectonic field of trend, but also seismic and inherited northwest-southeast direction faults can be activated. This earthquake raises new questions and comments while revised some established views. So, a low-angle active fault, neither Tirov-Navos fault, not the Elasona fault, not the Larissa fault or the Taricius fault activated, although have shown a weak surface phenomena. Maybe they activated its sympathetic structures, but the strange thing is that it's a very low angle, 36 to 40 degrees. And as we believe, this is a basal detachment fault. So there is all these new concerns and essential connections. The latest earthquakes seem to be associated with a direction field and faults that tend to create new structures in the area, providing the continuous and gradual geologic evolution of the area. In the area of Paleozoic, maybe in some thousands years or 1 to 2 millions, there will be a new valley. The state of the active stress and the strikes of the active tectonic structures, it is not so fixed that we knew up today. The existence of a seismogenic fault in a mountainous volume, in a mountainous area of crystalline rocks without typical geomorphological expression arise new questions. And finally, last but not least, which is the role of blind faults in seismic hazard assessment? Thank you, ευχαριστώ, teşekkürler, grazie, and later, if you like, I have a 7 minutes video for this, accompanied by music for the liquefaction of the area. Thank you for your listening, and I would like to hear some comments from the Riccardo Caputo, because it's the second homeland and the study area for 30 years.
Okay, thank you very much, Spiros. So I think you will show the YouTube video later on or now?
I beg your pardon? Yeah.
Will you show the YouTube video liquefaction now?
I will try to show you. I'm not sure.
Okay, because
it's a YouTube video. Can you see it?
If you share your screen, then we will see it, I think.
Yes. Can you?
Yes, now it's all right. Yeah, okay now. So maybe full screen. Yeah, that's great.
Can you hear the music? Just to relax before a discussion, before summarizing.
Okay.
Ricardo recognized the area because it's very, very close to his village, his wife village, but I say his village.
Orhan? Can you hear me?
Yeah.
Yeah. I take advantage of the background with the liquefactions to say something about, you know.
Okay, so I am also working on the concluding remarks.
No, about the
how linear are.
Yes.
By yourself, yeah.
The last earthquake in northern Thessaly.
Yeah.
This confirms what I was saying yesterday, that more and more earthquake geology investigations should be carried out in our countries, because we need to recognize, to characterize, to parameterize more and more with more detail as possible most of the seismogenic sources affecting the region. Obviously, even with earthquake geology, there could be a bias in the sense that investigators study more clear evidence, more easy, and this will make the difference. More clumsy area or more, you know, hidden faults, Spiro says, they have anyway. I'm sure they have some evidence, or the evidence could be obtained based on different methodologies, not just in the field with the hammer at the compass. Maybe we need to use different approaches, but I'm sure that insisting in seismogenic regions in general could provide some put in an effort, could provide some results. Of course, there will be always blind structures or very rarely activated structures that will remain a surprise. Our duty, I would say, as earth scientists, is to contribute to reduce these surprises and to improve, of course, the databases of seismogenic sources, and so contributing to improve the seismic hazard assessment analysis. As far as the Damacy earthquake is, I'm still waiting some more information in reality, because there is no relocation of the seismographic network around the area is. I mean, the permanent one is relatively poor with distant stations. Now is a little bit denser with the temporary seismographic network, but you know, we need relocation, or good relocation estimates, or better recalculations on the fault plane or the focal mechanism and so on. Anyway. The evidence was not as expected, let's say, with a 6.3 we expected normally a clear surface rupture, what with Spiros we called and we defined morphogenic earthquake. I mean, 6.3 in Greece commonly is referred to, or is this morphogenic earthquake. That is, it generates a morphology, it changes the Earth's surface by linear scarp. So it is not so clear at the moment. There are several kilometers long ground ruptures along the Tarisius river. We are investigating these structures, if they represent, if not the real, the entire displacement, or they account for the entire displacement along the deeper seismogenic source, they could represent at least a branch, a high angle branch from this low angle surface. We are investigating, we're making paleoseismological trenches to see if it is one shot by chance, let's say a purely sympathetic structure, or there is some recurrence in some repeated events that reactivated these structures. So the work is still in progress. I would say that we are still collecting data as should be, and we are still not very far, but anyway, we're not, we have not said the final word, and the conclusion are still far to be reached.
Okay, thank you, Ricardo. So, Spiros, do you have anything to add, Spiros, Ricardo's talk?
To the next meeting, to the next workshop.
Okay, so
because for this earthquake, maybe we will organize, Ricardo, in Larissa, both online and a meeting. All of you are invited to discuss, because it was a different earthquake. We were expecting in the faults that so well studied, morphogenic, typical morphogenic earthquakes, according to the terminology of Ricardo, but nature hidden.
Yeah, I agree. We expected a clear rupture for 10 kilometers.
No clear rupture, no. And Ricardo, the strange is that you know the area very well, on the Paleozoic, the mica schists and gneisses, and neither to the marbles, not to carbonate cover. We didn't find any surface in the carbonate, only in the schists, in the gneisses.
We will discuss it.
Okay, so we can now start an open session to complete the main issues of this workshop. As you know, Hassan and yourself, Ricardo and Spiros, have prepared the concluding remarks arised from this workshop in 2 days. If you wish, I can share the screen and show these concluding remarks for the audience, if you wish. Can I do that?
Yeah. Have you received the last? Yes.
Yeah, I've got the latest version of this concluding remarks. It may take a few minutes, but if you wish, you can maybe read on the screen, and we will finalize these concluding remarks of the workshop in Turkish as well, and may share from our website of the workshop in a few days, if you wish. Hassan, do you have anything to say on this concluding remarks. Thank you very much for your efforts in preparation of these remarks.
No, this is the last one.
Yeah, may need a few revision, maybe.
Yeah.
We could do that.
You can read it if you want.
Hassan, I have the yesterday conclusions you sent to us by email. So I will see them today, tomorrow, maybe tomorrow and after tomorrow, and some corrections or some discussion to be published.
Yeah, this is the improved one.
Yeah.
So we can also
make a press release, Orhan.
Yeah, also expecting from all the panelists, all the audience, their positive response, positive contributions to the preparation of this final conclusion of the workshop. If they wish, they can send their opinions, their comments, maybe through email to us, and we can revise this version and share it on our web page. But several important insights and action items were accomplished through this workshop. You can read one by one here. Hassan has summarized the presentations from each session here. Thanks again for summarizing these issues, Hassan. And an important lesson from the Samos earthquake is that the place where the most severe damage was observed in earthquakes is not necessarily the epicenter of the earthquake. In this case, faults assigned to these earthquakes and intensity distribution of earthquakes that occurred in historical periods should be reviewed. This is important. And the other important lesson is that the behavior of local soil conditions during the Samos earthquake. The soil under the collapsed building amplified the earthquake waves more than 2 times. Also, dynamic soil behavior during the earthquake moved away from linear behavior and showed non-linear behavior from an average depth of 55 to 60 meters that we experienced severely in Izmir in the Bayraklı district. So we would like to emphasize that every new scientific knowledge becomes more valuable when shared, and new possibilities are opened in the focus of making an impact within the approach of doing business together, while underlining the possibilities that can be achieved with the approach of working together and achieving together in the field of earthquake research. We would like to thank all the scientists who contributed to the workshop and wish them success in their impact-oriented research. So in this context, we have decided to make a special issue within the scope of TÜBİTAK Turkish Journal of Earth Science in order to make the latest studies on earthquake research in the Aegean region permanent. Participants at the International Workshop on Active Tectonics and Seismicity of the Aegean region, with special emphasis on the 13th October 2020 Samos earthquake, are warmly invited to contribute, but also any original study on the seismic hazard and risk assessment of the Aegean region is welcome. This special issue will be dedicated to the people who passed away during the earthquake of 13th October 2020 in Greece and in Turkey. So the guest editors of this special issue are Professor Spiros Pavlides, Ricardo Caputo, and Hasan Sözbilir. So thanks for accepting this invitation, our friends.
Orhan, may I Could you switch
Yes.
off? May I show the screen?
Of course, I will just stop the screen. Okay. back to 20 years ago.
No, 31.
Hassan, you remember this meeting? Where are you in this picture? So you are in the organizing committee, I guess.
Yes, I remember now.
In the ESCA meeting. So from right to left, Ricardo and my friend Haluk. He is retired now from the geological department at Sivas. And next to him, my uncle, Professor Yusuf Tatar, he is also a professor in geology. And the next to him, Professor Muharrem Satır from Tübingen University. You may know him. And Spiros, young Spiros.
All of us were.
All of us. All of us.
with very black hair. Thanks, quite a surprise. I ignore this photograph. Thank you very much, Ricardo. And Oran, Zeki Tutkun is playing violin.
Yeah. Dancing Sirtaki, I guess. And of course, on the right-hand side, Professor Zeki Tutkun.
Yeah.
Playing guitar, and the other side, on the left-hand side, Professor, I think, Erçin Kasapoğlu, from Hacettepe University. Okay, thanks very much, Ricardo.
Thank you very much. Now, it is the stamp of 31 years scientific link and friendship.
Yeah, okay.
Yes, and we will still continue.
Sure. So let me give you some information and also thank to someone who contributed to this conference very much. Well, first of all, the first day sessions were watched by more than 800 people on YouTube channel. This is important. So you can anytime still watch the sessions in 2 days on our YouTube channel. So please visit this channel sometimes, anytime you wish. So we will send a certificate of participation to all people and also the co-authors of the presentations in a few days, maybe. And of course, expecting your positive contribution to the special issue of the Turkish Journal of Earth Sciences in due course. As I said, Spiros, Ricardo, and Hassan will act as the guest editors of this special issue. First of all, I am grateful to the invited speakers and the co-authors of each presentation, the chairs of the sessions, Professor Ahmet Cevdet Yalçıner and Doctors Dimitris Sakellariou and Massimiliano Maggini. I would also like to extend my sincere thanks to Professor Hasan Mandal, the president of TÜBİTAK, Mr. Hamza Taşdel, and the president of AFAD, the rectors of the partner universities from Turkey, Greece, and Italy, Nükhet Hotar, Alim Yıldız, and Hakan Yekbaş, director of TÜBİTAK Ulakbim, Mr. Mehmet Mirat Satoğlu, for hosting us in TÜBİTAK Ulakbim here in Ankara over 2 days. So finally, my special thanks go to my dearest friends in the organizing committee, Spiros Pavlides, Ricardo Caputo, Hasan Sözbilir, Derman Dondurur, and my friends here, Cihan Aksop, and Fikret Koçbulut from Sivas, Mustafa Softa from İzmir, Murat Köreke. He did very much during these 2 days. He was the host of this Zoom broadcasting in 2 days, the technical staff of Ulakbim. And also here, Kınar Dündar, Seval Özgül, Bedia Bal, Handan Kurtuluş, Neslihan Karaköy, and many other friends from İzmir. They were in the kitchen of this organization, so this meeting couldn't have been held without their great efforts. Thanks very much again. So,
may I say a few words?
Yeah.
I would like to say congratulations to all of you that you organized this excellent workshop and all of those who contributed to its organization. It was this scientific bridge for dealing with natural disasters, and especially with the seismic phenomenon that affects the wider region of Eastern Mediterranean, where we live and create our countries. Let's try to continue it in the future.
Yeah,
it's worth it. It's worth it. During these 2 days, several papers were presented by various researchers that show innovation, new efforts, and penetrate into future problems that turn them into today in the context of an explosive development of our science. Let's remind from that period that show the photograph of Riccardo Caputo, 30. My career is 45 years ago. For the first time appeared the word neotectonics, later paleoseismology or active tectonics, and it was an explosive development. But we still have a long way to go. We still have a lot of problems. Nature likes to be hidden. And I would like to emphasize that in today's, in this international workshop of active tectonics and seismicity, especially on the Samos earthquake, the latest scientific studies on the seismicity of the Aegean region, earthquake hazard sources, the tsunami hazard, were presented and discussed among scientists participating in this work. And several important insights and action items were appeared in this workshop. To say the excellent section of tsunami and the progress being made in this area, in active tectonics, we have here so many groups appeared for and show us the results from the Samos earthquake. Very interesting work for some young Turkish scientists in the poster session. And I would like also to mention that the only common paper between one from Turkish side and Greek side was that of Onar Tan and Karakostas and Papadimitriou, and his last wish in the near future to have more common research, common presentations, and I hope, dear Oran and other colleagues, that the most of these presentations will be appear in the special issue. It's worth it. We will try the best to help during the reviewing all the people that they will going to submit the paper. I wish the most of these papers, because all of them, they have something to say, something, a little or a greater step. Thank you, all of you, very much.
Yes, thank you very much, Spiros. Yeah, this was a great experience for all of us. Of course, as you said, we should more develop the scientific and academic collaborations between our institutions and also between our countries in the very near future. This is very important. So I hope we will meet all together in a next meeting in person after the COVID-19 pandemic, maybe either in Turkey, in Izmir, or in somewhere in Italy, or in Greece, or in some other countries. So we should carry on. Again, many thanks for your great contributions, and see you soon. And tekrar görüşmek üzere, yakında görüşmek üzere. Maybe I can manage, so Kalime symptoma, is that right in Greek? See you soon.
Symptoma.
Symptoma, yeah. Presto in Italian, I guess. So I can't.
Oran, if you have every 4 months, 6 months, and every year an earthquake.
Yeah. So I can't.
In Italy, Greece, or it was the last earthquake in Albania as well. I work there. I was there many times in Albania as well.
You know, I learned some Greek language because my first presentation, scientific presentation in my academic career was in 1990 or 91 in Thessaloniki. You remember? I was so excited. And we had a very nice dinner at the end of the meeting in a garden of a ministry somewhere. You remember?
Yes.
So that was almost 31 years.
Karaburun Peninsula.
Yeah. Okay, that's all from my side. So floor is yours, Ricardo, Hassan, and the other friends now online.
No, it was just to thank everybody. It was a pleasure. It was a pity we could not. We tried to. We attempted up to the last minute to do it in presence. Would have been different, of course, but we cannot succeed. I hope for the next meeting to be in presence, really, because this is another stuff. So thank you, everybody. Thanks to the contributors. We wait for your contributions, written ones, submitted to the journal. That's all.
Thank you, Ricardo. Hassan, you have some words, yeah?
Everything was fine. I would like to thank all the presenters and the participants. And valuable information has been presented for 2 days. And I think this information will contribute significantly to the seismicity of the Aegean region. In this context, we expect all the scientists to contribute to the special issue that we will prevail in the International Division of Earth Science. And thanks again to everyone. And see you face to face in the next workshop.
Okay, so I don't know who is online now, but Derman is here. Derman Dondurer, he also made great contributions to the organization of this conference. Okay, so anyone who may wish to contribute, just we close the meeting. Okay, so hope to see you very soon in another meeting. And thanks again for joining us in 2 days. And hopefully we will have a very important contributions to our special issue in the near future and may publish it maybe by the end of this year in 2021, maybe in November or December. So thanks very much from now. Okay.
Teşekkürler, grazie.
Okay, thank you.
Thank you, bye-bye.
For everybody joining us in 2 days. Thanks very much.